انتهازية. انتهازية. Hallo, hallo. Ja, 1, 2. Za, ha, ja.
HDMI.
Good morning, everyone. Welcome. Okay. Then you are in control of the button. Okay. Then I'll blink at you. Good morning, everyone. Hope you found a comfortable seat. It's an amazing room here. We have an exciting block of AI, ML, AD sessions to be presented by bright intellectual minds of the Julia community. The first talk is about NeuroTree, a differentiable tree operator adapted for the treatment of tabular data, newly introduced in Julia by neurotrees.jl. A general operator composable with the building blocks of the Flux ecosystem in Julia. Please welcome Jérémy Dejani-Bouchard.
Thank you. Great, thank you. So I'm Jérémy. I'm the head of science at Ivovest, a portfolio management firm specialized in public global equities. We follow a systematic investment process, so that means we go from data to decision with little to no human intervention. This means that we rely extensively on predictive models and our ability to characterize future stock the future patterns of stock returns. To do so, our models are fed primarily by tabular data or multivariate time series that we represent as tabular data. For those kind of models, the dominant form of algorithm have been gradient-boosted trees for almost a decade now, thanks to XGBoost, but also other libraries like GBM, CatBoost, or Evo trees. Despite all the rage in deep learning, there hasn't been a strong contender that is based on our architecture that we use the traditional building blocks of neural networks like dense, convolution, transformer, or other attention-like mechanism. So the approach taken with NeuroTree was to start with what works well, gradient-boosted trees, and make the most direct translation into a differentiable flavor. And by doing so, the aspiration was to tackle some known limitation in trees. Two of them are that they are myopic, only looking at the immediate best split when we grow a tree. So that means that we ignore potential going for a suboptimal split, which might reveal a greater optimum down the tree structure. Another limitation is the representation capacity of trees. To illustrate that, let's take a look at this shallow tree of a depth 2. In such a tree, there's only 4% potential distinct values. So if we have a linear relationship between the feature and the target value, at the best, we can only get the staircase with 4 steps. That's not optimal, and we'll need a large number of trees in our stack in order to get a reasonable approximation for such linear relationship. And back to the tree structure, why aren't they differentiable? It's because that the split node, the 3 gray nodes that we see at the top, perform hard decisions. And they are, so for a given observation, there's only a single leaf that is mapped or associated to this observation. In this case, leaf number 3, as highlighted by the green arrows. Another perspective is that this tree structure gives us the information about the probability for the observation to belong to any of the terminal leaf. With classical trees, those probabilities are all zeros except for one leaf, leaf number 3, where the probability is 1. So NeuroTree, what we do is we start with a full, complete binary tree structure, and what we attempt to do is to learn the probability associated for each of the split node. Once we know the node weight, the remaining task to get a prediction is quite trivial. We just need to cumulate the node weight, take a view on the last node that corresponds to the terminal leaf weight. Then all we need to do is to do the dot product between those leaf prediction and the leaf weights. So those leaf weights, the sum of the weights have an probability interpretation. The sum is 1 here. So the remaining ingredient to get the differentiable tree is to see how do we have a differentiable or smooth node weight. As you can see on the top diagram, you might recognize the good old dense operator, and that's really all that there is to understand here. So there are 2 hard decisions performed in a split node. The first is to select a feature. That is done by doing the product of the dense weight times the input feature. So that acts as the mask over our input features. And then the bias addition allows to control the second hard decision, which is the selection of the threshold value, which will decide whether an observation is sent to the left or the right child. Finally, the sigmoid activation allows us to project this into the probability domain. And now we have our node weight. So the NeuroTree structure is not only about a single tree, but a collection of trees. So all we need to do is to concatenate the learnable parameters all together. And these are all the learnable parameters in a NeuroTree. So the first 2 are the learnable parameters associated with the dense-like operation. And the third one is the leaf predictions. Computing the node weights is the compute-intensive part of NeuroTree. Yet the algorithm itself is pretty simple, with a little catch is that it performs element-wise mutation, which is tricky for autodiff systems, as you're probably aware. So the solution is simply to go for implementing custom gradients by using chain rules, both on CPU and GPU. So what I've described so far is an actual simple neural network operator, similar to what we can find in the NNLib library. So the neurotree, as you can see here, can be built just like a dense operator, specifying the dimensionality of the input features and of the output feature, as each leaf can output an actual vector of predictions. In neurotree models, we bring some helper in order to build actual models, which are just a simple flux chain. So in its simplest form, a neurotree model is just a chain that is composed by a batch norm followed by a neurotree operator. Neurotree models implement a MLJ compatible API as well as an internal one in order to help in some cases where we want to have easy access to early stopping mechanism by tracking a metric on a evaluation data. Does it work? Well, we perform a benchmark on 6 common datasets of varying size. Common datasets found in benchmarks that we found in XGBoost and CatBoost own benchmarks. And what came out is that neurotree was the single best model on both the year dataset on regression and also the boson-Higgs classification problem. Noteworthy is that it was competitive with all the other classical gradient-boosted tree libraries on small datasets, which is not usually the best kind of condition for gradient-based models. On the flip side, on the ranking task, it wasn't as great. So the reason for that is not on the task itself, but likely more about the nature of the data. So for example, if there are missing values or unusual skewed distributions, this is where the soft decision process might be less than ideal than the hard decisions that the classical trees give us. An interesting aspect about the algorithm is that it can bring more signal diversification. So what is shown here is the correlation between the prediction between all of the benchmark algorithms. So on the lower left, you can see darker colors, which match lower correlation, which means that there's a higher ensembling potential by using its signal. So finally, some future direction, performance optimization, always, better support for categorical features through embedding, integration with enzyme in order to get rid of the custom gradients, and finally expand the scope of the neurotree models in order to be a more general engine for tabular data. So I hope I managed to cram everything I wanted to say in time.
Thank you for the talk. Let's give applause. Now's the time for the audience to also ask questions.
Thanks, fantastic package and talk. I'm from particle physics, which provided you the Higgs boson benchmark. So we were fascinated by the paper you cited, which shows you that sometimes table performs better, decision tree performs better or even better than deep learning models, and we have papers in our field observing similar things. So the question is, what kind of intuition should we have on these different tree models and about their performance? And also, I mean, if you can't answer in just a few lines, maybe some kind of literature pointer would also be helpful. Thank you.
Oh, thanks for the question. I couldn't point to a literature pointer, although there's some paper about like why tabular models tree models still outperform deep learning models on tabular datasets. Otherwise, I think it's like the ability to efficiently navigate through like the large feature space, like in tabular data, like each tree is a different dimension, and I think the tree structure is quite efficient as navigating this feature space. And I think there's something that made some noise about like Kolmogorov or Arnold structure that I think was an interesting kind of perspective about navigating those kind of dimensional data feature space common to tabular data. So that will be like just my quick answer, but happy to explore more after.
So in a regression mode, is your output then smooth?
Yeah, the smoothness comes from the fact that the probability associated with each of the leaf is smooth. So that means that if the association, so the prediction in a leaf is a constant, but given that an observation, if you tweak, for example, if you move on a given variable, it's not a hard decision going into left or right. So by increasing a smooth increase in the probability of belonging to that leaf, you're able to get a smoother output from a differentiable tree. That's it.
Thank you. Let's give applause.
Oh.
Next, young talent, Tim Siebert from the Technical University Berlin mathematics program will share news about the newly developed package adolc.jl that challenges the current use of algorithmic differentiation. adolc is a general-purpose AD, combines various functionalities, and offers convenient usability in Julia. Please welcome together Tim Siebert.
Hello? Yeah, hi. And welcome to my talk. I'm Tim Siebert, and I'm a master's student in mathematics at the Technical University of Berlin, and I'm working as a student assistant at the Weierstrass Institute of Berlin. And part of my master thesis was the implementation or the wrapping of the C++ library adolc, where I was mainly supervised by Jürgen Fuhrmann and Andrea Walter. In my talk, I explain you why we have implemented adolc.jl. I will introduce a method that is, to our knowledge, currently not available in Julia, the ABS linearization. Then I will go briefly through the API and explain future steps. So yesterday, we had a nice talk by Adrian and Guillaume, and they told us there are already a lot of AD packages out in the Julia ecosystem, and it's quite easy to get lost when you have to select one. And yeah, here I am and present to you a new one. But actually, that's not fully true because adolc is a quite old package, which was originally written in C++, like 30 years ago. And it's also quite well known in that area. And one key aspect to implement adolc.jl was to enable people that use adolc in C++ to shift maybe more easily their codes to Julia. In addition, there are some key features which are currently not that available in Julia, like a focus on tape-based forward and reverse mode, and especially on the combination of them to compute then, in the end, higher order derivatives. And adolc does this also by using univariate Taylor polynomial propagation, but univariate Taylor polynomial propagation in the isolated aspects are also currently available in Julia. So, and also there are methods like the ABS linearization, which is not available in Julia but implemented in adolc. In addition, we focus on a kind of intuitive access to the derivative computation. So the ABS linearization is basically a possibility to compute a piecewise linearization of a non-smooth function where the non-smoothness comes from an absolute value function. And with an ABS linearization, you can compute certain generalized gradients or Jacobians and use them in Newton steps, for example. In addition, the convergent properties of the ABS linearization is quite well understood, and there are, for example, second-order approximation properties. Also, an important aspect is that it's quite easy to introduce this to a forward mode system. For more information, you can find this in the paper, which is in the presentation. The API of adolc.jl, first focuses on, we want to make the adolc methods available in Julia. Then we want to summarize various AD methods in some kind of intuitive drivers, or one driver where you can access the different modes. And the first idea is to use, or the first main function is the derivative function. You can specify a function, the derivative evaluation point, and when you, for example, want to compute a Jacobian matrix product, you do this by specifying this symbol. And the right multiplier, so the matrix in the Jacobian matrix product, is given by dir, which is short form for direction. And when you have, for example, Jacobian vector products, you can understand it as a directional derivative. That's why we call it dir. And then you just get the results by plugging everything into the derivative function. For first order derivative, there are a lot of, there are various possibilities. For example, also the Jacobian vector product or a vector Jacobian product, which is usually also implemented in forward and reverse mode packages. But there are extensions like Jacobian matrix and matrix Jacobian products. Second order derivatives can be computed in the same way. And for example, if you want to compute a matrix Hessian matrix product, which is a tensor product, you in addition have to specify weights, which is the left multiplier, and then give this to the derivative function. Also for this case, there are a lot of more possibilities like a Hessian vector product, and you can find all the possibilities in the documentation. There are also drivers for higher order derivatives, which can be accessed quite easily. For example, you can pass a list of partial derivatives in the following form. This partial derivative in the middle gives the sixth derivative with respect to x1 and the first derivative with respect to x2. And then you give the list of partials into the derivative driver and can access them and get the result. You can also just giving a degree to the derivative function and end up in the full tensor. I mean, currently the compressed tensor because you want to avoid similar values which occur because of symmetries. And then because LLC computes higher order derivatives based on univariate Taylor polynomial propagation and some cool mathematical tricks, you can also do Taylor polynomial propagation, univariate Taylor polynomial propagation, but this is also available in other packages. Future steps will be to integrate LLC.j into the existing Julia ecosystem, AD ecosystem, for example in AD types or the differentiation interface.j. And then we want to add more functionalities from LLC, and if you are aware of some functionalities which you want to use, just open an issue. And that's it. Thank you for your attention, and please feel free to ask questions.
Thank you. Anybody has a question on LLC? For example, which industry sector would the application of these methods most benefit within the upcoming, let's say, year or in the near future?
I mean, every part when you want to do some optimization, for example. For example, in electrical engineering, when you have, for example, more smoothness in the functions, you can do some optimizations over the non-smooth functions with a linearization.
We still have time for one or two questions. Anybody from electrical engineering or highly sophisticated positions in AI, ML? Don't be shy. Thanks to Tim for enriching the Julia community. Let's wish him best of luck. In the next 30 minutes, Jan Schimmel will evangelize us about generative AI in Julia. It is an invitation for curious minds to explore, learn, and contribute to shaping the future of generative AI in the Julia ecosystem. Without further ado, let us invite Jan Schimmel.
Thank you very much for the intro. So just out of curiosity, how many people here use GenAI daily? Just raise your hand. Okay, that's pretty much like our survey. And how many people have actually built a RAG system? I'll explain it later. Okay, fewer. Okay, so everyone has something to learn. Cool. So let's start. We'll give you some confetti, like Jack earlier. It's the beauty of Quarto. So a little bit about me. As you introduced, I'm Jan Schimmel. I work on decision intelligence at LexisNexis. What is it? Well, pretty much it's making data turn into profits. In my experience, a bit of a mixed bag, but in the past year and a half, I have basically become a professional string wrangler. With Cameron, we have co-founded JuliaGen AI org, so we can kind of formalize some of the Gen AI efforts. We have some great Google Summer of Code students, and I'm also the creator of promptingtools.jl, which I will talk about later as well, and a bunch of other projects. I do have to say that this talk represents my personal views and not those of my employer. So, agenda. I want to talk a little bit about why this could be interesting to you, whether you're convinced or not yet. I will try to pepper it with a lot of little demos and tips, so you probably can get some ideas out of that. I will also mention how to build successful Gen AI systems so that you have a recipe that you can follow, which no one ever does, but hey, if you do half of the recipe, that's already pretty good. And I will try to leave time for questions in the end, so you can like roast me properly about all the hard questions you have on Gen AI. So, yeah, one thing I should say, I will not have a slide about why Julia is the best for Gen AI. I know it's a bummer. I had a slide like that in my JuliaCon talk last year, so you can check that if that feels good. But what's important to know about Gen AI is that it's pretty much just sending requests to these online models. And what you tend to do as a programmer is really just wrangling the strings around it, right? So you need much less from the language, which is kind of different than a lot of the things we have heard about in this conference. So kind of keep that in mind. So what is generative AI? What I want to call out here, as the name suggests, it generates things in the end of the process usually. But the thing to know is that it's not always just text. It can be images, video, or any other content, right? So they say picture says more than 1,000 words. I'm not sure what it says about videos, but this is what I thought my presentation will look like. This is generated with Runaway new model. So as you could see, there was a grass and a few more people. Well, that's some weirdo. There was a grass and a lot of people. So yeah, you can tell Gen AI does not predict future. Yeah. How do I escape this guy? Okay, cool. The other thing, it's really unbound for your creativity. So like if you were ever wondering what your pet would look like as a superhero, well, this is a 3D model generated with Hyperhuman. You can do actually quite high-res resolution renders of 3D objects. If you're into games or anything like that, that's actually pretty exciting. The amount of work that you would have to do in the past is just unreal. So why should you be interested? There are broadly 3 areas that I see, and then a lot of them that I won't mention, which would have kind of a lot of similar use cases. So it might be literally for your leisure. It's a lot of fun, and like I said, there are no limits to your creativity with the tools we have now. There's productivity, right? Nowadays, you can literally buy time by using some of these tools. You pay a very little, cents, and you can save minutes and hours. And the third one business. There are a lot of exciting things you can do, and I will mention examples of each later on. There might be a lot of other motivations. There is social impact. You can help a lot of people now. You can do cooler research. I have seen successful AI therapists and things like that. So this is not the only things you can do. I just wanted to call out some of the main ones. So when it comes to leisure, I'm going to shortchange you here. You can already generate a lot of short clips, songs, novels, whatever it is that you're interested in and you like to spend your time on. With the demo, well, I already showed you video, so again, I'm going to be saving time here. But yeah, just open those websites. You don't even have to pay most of the time because they are desperate to get users, and you can just try it out. It's actually unreal what you can do. And I have a tip for you. I presume every one of you is working on your Sonic Pi game, right, to become a DJ in your spare time. But let's say you're not that good yet. So at your next party, literally pull out suno.ai and have everyone pitch in with like, what would be a cool idea for some lyric? What do we want to talk about? What happened at this party? And then come up with some crazy style fusion. I want a techno reggaeton. And just see what it produces. It's actually a lot of fun. Highly recommend. Yeah, that's the sort of parties I go to. So arguably the biggest reason why I created the prompting tools package was the productivity. Because Julia is by far the best language when it comes to time to results, right? And I felt like I need generative AI to be part of that story. Otherwise, Julia would be just left behind. So what are some of the use cases? Well, if you have to, I don't know, find an email for your dentist to change your appointment, you have to draft an email for it, right? Like all those little admin tasks in your life are just like wasting time that you could spend doing something more meaningful. So you can actually automate a lot of that already. You can obviously speed up coding, whether that's kind of for fun or whatever you do. And you can also do brainstorming. It's actually much easier to critique something that gets produced by the model that you can then build on. Right? It's a great unblocker when you're kind of stuck. So as a demo, let's see how well that works. I have Proto Portal here. Before I get into that, I don't know if this is big enough. Is this big enough? Okay, can you actually see that? I want to say in Julia, we love REPL, right? So when you actually import the prompting tools, the first thing you can do is literally send any questions to the large language models literally from your REPL. How bigger is bigger? Is this bigger? Like grandpa. Oh. This? Nice. I'm not sure you're gonna see much. Anyway, so literally like silly question, not something I ask every day, but like literally straight from your REPL, you just press it. I'm caching in the background because I didn't trust the Wi-Fi. I have trust issues. But like you can see, you immediately get a message, and here I get a snippet of literally what is the function, but also the exact thing I wanted the function to do, together with some inputs, so I can even try it does the right thing, right? So that's how simple it is to get these like small answers immediately where you are. But soon I actually realized that that's kind of not enough, and I actually like to have a separate app on the side, and that's where the Proto Portal comes in. So I guess most of you know this, but Proto Portal, Prompting Tools Portal. So when you see it, well, pretty much looks like ChatGPT, so why the hell did I rebuild ChatGPT, right? Well, big mistake, ChatGPT doesn't support Julia. Here you can execute Julia, you can even have the model auto-fix it, so you don't waste your time on copy it here, run it, there's an error, send it back, fix the error. All these things it does automatically, right? ChatGPT doesn't do templates. Like if you have used GenAI, you probably have a set of instructions that you like to copy paste. It's such a pain to copy paste. So you just ask for whatever template you want. Like I want to draft an email. Well, I have my email the way I like to draft my emails, right? All this is in prompting tools, already a bunch of starter templates, but you can add your own. My wife, for this tool, we host it separately so we can use it from our phones and everything. She has a bunch of her templates. Right? Because she has a way how she likes to talk and everything. And there's a lot of other advanced stuff that this thing does that ChatGPT could only dream of. But like as an example, I also like to use text-to-speech. I'm not sure if you guys tried it. You can talk twice as fast as you can actually write. So you can save a lot of time. So draft an email to Tom that I'm running 20 minutes late, and I think it's best if we postpone that meeting until next Tuesday. Make it friendly because I know him well. And you just have it, you type it in, you can add however much context you want, it's already generated, right? Oh, there are some ugly bullet points because most of my emails are with bullet points, my team kind of knows. Remove the bullet points, he's a really good friend, just make it chatty and friendly. Well, the chatty didn't get transcribed very well. Well, and this didn't work very well. That's because of my caching. I'm still tuning that feature. That basically, a lot of questions that you ask repeatedly, you just don't want to pay OpenAI for, right? Because they cache it for you, but then they charge you for it. So like, why would I do that? But yeah, basically you can iterate it very easily. And hopefully this gives you ideas of what you can use it for. So back to the presentation. So what should you try? So try to write a script, how to actually find an email address online of, I don't know, your dentist, whatever that is. And actually draft the email to that address with something you want, right? Just make a tiny command line interface where you just type in, write this, search this, and it kind of does everything for you. It's a great practice, and those are the little automations that maybe if they're really good, you can start sharing with the community, right? Maybe more people would actually like to use something like this. This is the example code. You don't have to read the details, but pretty much that's everything you need to do to build that, right? You will create a web search. It looks for the email address, grabs the email, grabs all the web results, extracts the email address, drafts the email for you. That's kind of all there is to it. Is it going to be the best email? No. But this, once you build it, will take you 20 seconds. So that's a pretty good start. So the third area is arguably the most exciting area, right? Because your tools that you build and the applications will have to be a lot more intentional and a lot more robust, right? This is not going to be a productivity tool that you put in a script and you're done. But like the impact and how much you can scale this and how much value you can deliver is actually unreal, right? Imagine you have 1,000 people and you save them every day from reading one long email, right? That's 5 minutes. If those 1,000 people save 5 minutes every day, that's the same amount of output as literally having hired 10 new people that will work in the company, right? That's how big the impact can be from something as silly. So yeah, very exciting. So some use cases here for you. Well, data processing, so what is that? Well, finally, you can actually extract the notes from the sales calls and all the various things that happen around the business and actually get a lot of value out of them, right? You can increase the share of the useful data in your business because, you know, SharePoint is where documents go to die. So you can actually finally start tapping into a lot more of that data that your business has. Like this is probably all the data you have, and like this is in your database, and you know what the columns are, right? This can grow. You can expose a lot more to people. Reducing UI barriers and system barriers. Well, I don't know how about you, but I have to enter my performance objectives in 3 different systems. It's a lot of fun. I love it. And as a user, you know the feeling when you come to a new product and there are like all these UI elements everywhere and you have no idea what to do? Well, imagine as a new user, there's going to be box. I just type in, this is what I want to do. I don't care about your UI. Just like, this is what I want to do, right? And it literally does it for you the first time. And then you start to learn the UI. So that's something you can do for your users and also internally. And then obviously there is code search and everything. Like you don't need a year to ramp up the developers in your business because you can actually get the right pieces of code base to them very quickly and very efficiently from the day one. So demo here, I chose AI Help Me. It's a package you can use already. But the reason why I chose it is because I think it's relevant in any context. It will show you that RAG paradigm. It stands for Retrieval Augmented Generation, which is basically fancy talk for I'm going to put the right data in the prompt. So AI Help Me, right. So AI Help Me basically can grab information and from documentation of any package in Julia, right? And for a bunch of packages that are quite popular, we actually download the documentation and prepare it for you. So when you literally start with AI Help Me, you can already see all the Julia documentation, Maki, and a bunch of tidier stuff as well. And we have a Google Summer of Code student, Shreyas, actually working on bringing much more packages and making it much easier. So what would be a use case? I love algebra of graphics, but my brain just refuses to learn all the keywords. So every time I use it, I literally had to use like a separate window with the documentation to like know how do I change something about the limits of the y-axis. So AI Help, how to rotate axis labels as an example. Ignore the p-print, you don't need it. That's because I'm doing some shenanigans under the hood. Basically, you ask the question and it answers like before, right? It feels like the same thing, but it's actually different here because we are putting all the right pieces of the documentation inside of the prompt before we send it to the model, right? So that actually allows us to do a lot of cool things. Do I have another question? I have a bunch of random stuff I did before. But like if I wanted to, I always struggle with the axes. Yeah, changing parameters of axis parameters, right? How do you do that? Another example, we can obviously pretty print it to actually see what's in. But you might be wondering, well, how do I know this is not hallucinated, like all the stuff on ChatGPT, right? So because Julia is so fast, we can actually do a lot of clever things under the hood, right? And this is kind of some of the advantages starting to shine. What we can do is literally expose more of that information and just have Julia calculate, well, what are the pieces of information are new? Where are the information pieces coming from? So if I see this like code snippets, right? It comes from the block one, which in this case is literally like this URL kind of underlying that knowledge, right? I see that the score between 0 and 1 is pretty high, so I have a high confidence that a lot of that came from there. And I can even see these highlights when there are words that we are kind of not recognizing that the model kind of made up, right? It might be okay, but like you immediately know this function name, is it made up or not, right? Which is something you don't get everywhere. So I hope that kind of demonstrates some of the things you can do. And I will give you also a quick sneak peek of, yeah, this one. There's another tool that might be helpful if you start meddling with GenAI. And the tool is called Spehulák. It stands for Spy Snowman because it kind of keeps your system cool and you can't see it. Yes, someone told me my package names are boring, so I try to mix it up. So what you see here is basically we are automatically saving every conversation in the background. So I can actually now have a look what exactly went to that model. We even have a view specifically for the RAG applications to really debug them and understand what happens, but I think this is good enough. So as a sneak peek here, we see kind of what template have we used, what model have we used, all those things. You can literally see the prompt that went to the model. This is literally the information that we then compress and send. So these are the instructions, this is the context, like this is how it looks. This is what we dump on the models, right? When you wonder why they respond badly, start here. Usually you're giving them something that's horrible. Like it's random, like what does it figure out, right? But it noticed this axis parameter and that's what it used for its answer, right? So that's kind of how you can understand these systems better as well. So I figured it's worth mentioning. So back to the tips. If you want to try it yourself, build a chatbot, integrate it with like a complex SharePoint site where you know there is a bunch of interesting documentation, and just expose it to your colleagues. You can put like a Slack or Teams around it. If you're wondering how much effort is it, well, once you have the information processed, it's actually as little as these 2 lines. That's all it's going to take to build the first RAG and start asking questions about it. If you're wondering when and how often GenAI is used by the community, we ran a little survey just before. And kind of one of the big learnings was actually that the daily and several times a day usage of GenAI was actually more than half of people, which is roughly how many hands I've seen in the air. The other insight there was actually that the professional segment, the yellow part here, that significantly goes up when it comes to that usage several times a day. That's most likely, my guess would be the code assistants. If you're not using any of the editors, copilots, or even Cursor, which is probably the best thing I've seen so far, give it a shot. And one other thing, we also ask, what are kind of the challenges that you have with building Gen AI in Julia? And by far the biggest thing is kind of things we've always heard, which is ecosystem. The ecosystem immaturity being kind of highlighted. The others were time, knowledge, and external kind of pressure when your boss says you can't do Julia, type thing. So let's talk about how to actually you can build things today. And I will also mention some of the gaps you can focus on. As an example project, I'm going to take the AI Help Me. I'm going to skip all these definitions. You can have a look at the slides later. Like I said, retrieval augmented generation means put the right data in the prompt, right? So the model doesn't have to make it up. The best approach I've seen so far for actually building any application is called eval-driven development. It's very similar to TDD, but it's kind of customized for the Gen AI. One thing I will say here is this talks about the Gen AI piece of your system. Anything serious you're going to build is going to be the system that you built and the Gen AI code, right? You will spend majority of your time building everything else, but this talks about that kind of the beating heart, how to make sure it's successful in the long run. So you will want to start with a canary prompt, which is literally pick a simple case. In AI Help Me, it can be how do I label axes, a y-axis in algebra of graphics. Copy paste literally the pieces of documentation that are relevant in it and send it to the model and see if it responds. You're basically trying to figure out, does this even make sense? If everything is right, does the model know how to do it? Pick the best model you can to basically validate the idea if it's sensible today or not. It can save you a lot of time. Then you do 3 to 5 vibe checks where you basically build a set of harder examples, some harder questions. You will still build it all manually, but like you want to figure out what are some of the edge cases, like what are some hard things that I can ask, and then everything you change, you will check every single one of them. When you change your input a little bit, you will run every single one of them. You still want to see how it basically performs on everything. If you're changing your prompts with one question, you will go in the wrong direction very quickly. At that point, you should kind of know what you're optimizing for and what you're solving for. So you should kind of commit to it. And as the next step, that's when you start bringing the RAG, right? You start like looking up all the documentation. How do I pick the top 5? Like that's kind of where prompting tools will help you a lot. But like this is where you pipe it all together. And again, you keep doing these vibe checks, right? When you build it. That's how you know you're kind of on the right track. That's when you quickly see when something goes off the rails. And then finally, you actually have to, in some cases, manually build 50 to 100 gold test cases. That's what you're going to be running all the time to really see where is my system failing. You can often synthetically generate them, but you kind of need to know how. There are a few blog posts I have on that. And then you just iterate from there, right? Again, constantly going after the test cases. Why do you need all these evaluations, right? Why can't you just build a prompt and see what happens? It's because, first of all, you wouldn't know if it's broken, where it's broken, and then when you fix it, you will not know whether you improved it and if you broke something else. That's kind of why there's this systematic approach to it. That's how you go from fun demo to actually something you can release to people in your business. In the interest of time, I'm going to take this one quick, but I just wanted to highlight basically what is the tech stack? What are the packages that we use? Again, this is what either the actions will be, what your user will see. This is majority of your code. If you want some simple UI, by the way, definitely use stipple.jl, super quick. The AI Help Me package even has a really nice GUI that Pere from the Genie team put together. But like, this is the Julia and everything else. This is where your business magic is. This is where you put all the checks and guardrails to make sure the bad inputs don't make it in, and then the bad outputs don't make it to the users, right? This is the magic, and we try to give you some tools in here. This is the GenAI core, where you would use the prompting tools, and for the RAG, it would be the module RAG tools. And then this is just kind of the LLM layer where we just send the packets and get them back in. You can build all this just with http.jl and JSON tree. It's just like, as soon as you want something meaningful, you will basically have to rebuild the rest of the stack. Over long run, you will want to evaluate and monitor the system, and also you will want to think about the inference. You saw Spehulag before. So what are some areas ripe for contributions? We have some amazing DSLs. It might be too early, but like this is where we can share a lot of efforts, because this is most of the work. Here, we're missing Pydantic. I'm happy to talk about it later if someone is interested. But like we need a way to handle all these strings and be able to say, this is the schema of what I would want, and then get it back out of it and validate it and have nice errors. Julia's type system is so good that we didn't need Pydantic pretty much until now. And inference would be nice to have. I think that's a commodity. I would be happy to sacrifice that. And then on the monitoring side, you saw the OpenAI API talk. Definitely, we would need some wrappers for these services. So conclusion, come build with us. Whatever you're into, whatever your motivations are, it's fun. It can save you a ton of time, except for the sad faces of my team over there. And it can unlock incredible economic benefits for your business or whoever you work with. If you don't know where to go, check out juliagenai.org. We have a Slack, Generative AI, where you can ask any questions, discourse, community calls. And if you're always curious what's up, Awesome List is where we kind of put all the noteworthy projects and everything that's relevant. And remember, all these models will only get better, right? So whatever doesn't maybe work today or is not good enough, it might be tomorrow. Thank you.
Thanks to Jan Schimmel. Let's give applause. It's impressive how much time this generative AI can save, even for an ordinary person. And I'm sure there would be someone who would like to get some advice on maybe already some of their incentives to save time and increase productivity, even for an organization. Anybody has a question on this expert?
So I'll do the more of a comment than a question thing. But so this is an extremely good package. Like, I don't know if people have used a lot of generative AI stuff, but like I've worked a lot with this, and like I've tried to do a lot of like Python stuff because you kind of have to. And like this is extremely easy to use, and it's like full of all these like very nifty little features. And so I just wanted to like thank you, Jan, for building something that's extremely cool. So yeah, so that's what I got.
I paid him to say that.
Yeah. Thanks, man.
I'll buy you beer later.
How do you compare this package to LangChain?
It's way smaller because it's mostly my effort and from Cameron and a few other people. So our area that we cover is way less. What we try to pick is basically what seems to be the best way to do something. What is the best approach that we hear about constantly, and then we put it in. That's one thing. The other thing is, I think they've done amazing work to get everyone started quickly, but they also created a ton of abstractions everywhere, which makes it kind of hard to understand what goes on in the end. And that's why I showed you the tool like Spehulag, that like you fundamentally want to understand that you throw some string at it. If that string is bad, if you put the wrong information in, the whole thing's bad, right? Like whatever you do. So you want to have that like feeling of knowing what you're doing and be able to go anywhere in the stack all the time. So the philosophy of prompting tools was basically allowing you to like plug in anywhere you want and really understand what exactly is happening under the hood, which I think is slightly different from how they did it. But most importantly, it's in Julia.
All right, thank you.
One thing to add also is why I'm excited about Julia in this is that you saw that most of the effort will actually not happen in the Gen AI, right? You just call some model somewhere, right? It's going to be the systems you build around it. And again, Julia is incredibly good for writing good, simple code to achieve potentially really impressive things.
We have time for another question.
If there is no more questions, maybe you can reach out to Jan Schimmel later, and let's give him one more round of applause. What will come next is 10-minute break, so please be welcome to come back in 10 minutes or so for another block of sessions. I am very, very sorry. We have one more session before the break. I looked into the wrong place on my laptop. Please come back for one more session presented by Darren Colby. This will be a 30-minute session. Sorry about the confusion. Let's get a comfortable seat. So this last session before the break will be presented by Darren Colby. He is another young student, this time from the University of Chicago. Darren will tap into the causal inference and the advantages of causal machine learning. Darren will introduce the Julia package causal ELM that implements causal estimators based on extreme learning machines. Let's please welcome, with applause, Darren Colby.
Thanks for the introduction. Gen AI, that's going to be a tough act to follow up. Quickly, before we get started, I just want to add that we're going to go through a couple examples. And if you want to follow along with those examples, there's a couple notebooks that you can get on the repo, and you can find those just by scanning this QR code here. So quickly, we're going to go through, for the agenda, what we're going to cover is very briefly and non-comprehensively what the potential outcomes framework is. Then we'll go through a couple motivating examples of how you can use causal ELM within this potential outcomes framework to estimate causal effects. And we'll tie those examples into this general workflow that you can use causal ELM for. And then we'll finally get into the mystery of what the ELM stands for in causal ELM. We'll quickly talk about, besides what we went over in the examples, the other estimators that you can use within causal ELM. And we'll compare it a little bit to some other packages, especially Python packages, and just talk a little bit about the overall design philosophy of causal ELM. And then I'll talk about what I see potentially as the way forward, a little bit with causal ELM, but more generally with causal machine learning in Julia. So briefly, this is going to be the potential outcomes framework. So some of you may have been in the really interesting talks yesterday or throughout the week on causal inference based on structural causal models. I think Sefer had a talk on that, which was really great. And that's to say that this potential outcomes framework is not that at all. So I just want to clear up any confusion and just say that potential outcomes, not structural causal models, and this is not better than structural causal models. It's not worse. I think there's great use cases for both, but this is just a different way to think about causal inference. And so under the potential outcomes framework, you'd usually be given a data set. So you'd have some covariates X, some treatment statuses we'll call T, and some outcomes Y. And so for each unit I, which can be a person or maybe a town or a village, as we'll see in one of the examples later. We'll define xi as a vector of covariates for each unit I, and ti will take a 0 or 1 as a treatment indicator, and just to keep things simple, but actually it can be categorical or even continuous, and some of the estimators here in Causal Elm actually do allow you to use categorical or continuous treatments. And so when unit I is treated, for now we'll say ti is equal to 1, and when unit I is not treated, we'll say ti is equal to 0. And then this means, so our outcome is going to be a function of the treatment. That's why we want to estimate the causal effect here of our treatment. And so we'll say when yi, or when unit I is treated, then yi ti, we observe y1, and when unit I is not treated, we observe y0. And these outcomes y1 and y0 are what we call the potential outcomes, hence the name potential outcomes framework. And so pretty simply, we can see the impact of treatment for unit I is just this tau I. It's yi1 minus yi0. So in theory, that's pretty simple, but we have a really big problem, which is usually called the fundamental problem of causal inference, which is we only observe yi1 or yi0, but not both potential outcomes. So like if you were doing a study, say a randomized control trial, you wanted to see the effect of some medication on some disease, and you had a unit assigned to a group that actually gets the medication, but not the placebo group. Well, you can't see like what that, or the problem you have to solve is that you can't see what the outcome would have been for that person had they been assigned to the placebo group, because you can't be in the placebo group and the treatment group at the same time. And so basically most models that are working under the potential outcomes framework either use some simplifying assumptions or leverage some knowledge about the structure of the data set, or use some clever research designs to try to overcome this problem. And so one example here that policymakers might be interested in is learning the effect of 401k plans on people's net worth. And in case you don't know, 401k plan is a sort of pension plan in the US. It's a private pension plan that employees and their employers both invest in, and once the employee retires, then they can withdraw money from this pension fund and use it to live off of. And so it would be very interesting for policymakers to know whether this actually works or not, and how they should or shouldn't regulate it. And so here we want to estimate the expectation of tau I, or the expectation of yi1 minus yi0, which is usually referred to as the ATE, or average treatment effect. And this was actually done a while ago in a study in 1994, the year I was born, by Poterva et al. And so in this study, we have xi, and it includes a bunch of characteristics about the individual employee. You can read those there. In this case, TI denotes eligibility for a 401k plan. So in TI is 1, the individual is eligible to receive a 401k pension, and 0, the person was not eligible. And then YI here represents the net financial assets in US dollars. 1994 US dollars. And so typically the way you could go about doing this, and I think how it was done in the original paper, is you could just use a linear regression, assuming you have randomization, or at least conditional randomization. But an issue there with linear regression is if you have, and especially when you have more covariates, if you don't know the functional form between the covariates and the outcome or the treatment, then you can get a biased estimate. And usually in like econometrics course, you'll hear, well, we can use prior knowledge or domain knowledge, but in reality, we usually don't have domain knowledge of whether we should use like the square root, or the log of some variable. But more recently, there's been this approach called double machine learning by Chernozhukov et al., where we actually don't need to specify a functional form. So we can use any machine learning models to estimate the treatment and the outcomes out of fold and get residuals, and then combine those residuals into a final linear model. And yeah, we don't need to know the functional form, and it works well with high-dimensional data. And so how can we do this in Causal Elm? So first, we're going to instantiate a model. So we just call double machine learning, and it needs to take at least 3 arguments, which will be x, t, and y, which are covariates, treatment, and outcomes. And there's a lot more keyword arguments that you can add in. If you are interested in seeing them, you can go look at the documentation. And once we've instantiated our model, we can just call estimate causal effects, or estimate causal effect, and in this case, we'll get back a scalar which represents, in this case, the average treatment effect, the effect of being eligible for 401k plans on net financial assets. And of course, you probably, after you've estimated your model, you want to get a summary of the model itself. And if you're coming from R, this probably looks familiar. You do this with like lm.summarize or something, and the same thing applies here. And you get this dictionary with a lot of different things that will make a little bit more sense later when I talk about what the Elm is in Causal Elm, with like activation function, quantity of interest here. We can see we're estimating the ATE. And one thing to note here is that these standard error and p-value here are set to NaN. And if you don't want them to be NaN and you want to estimate them, you can use the keyword argument inference and set it to true. But the reason that it's set to NaN now is because it does take a while to run, because a lot of the models don't have like closed form confidence intervals, and so the way we estimate these non-parametric p-values and standard errors is through randomization inference or permutation-based inference, and that takes a really long time. So by default, it's set to false. And so arguably the most important step in doing causal inference isn't estimating the effect, but it's actually validating your model, seeing how robust it is to violation of your modeling assumptions, or at least whether those assumptions that you're making are plausible. And so you can easily do some robustness checks in Causal Elm just by calling the validate method. And so in this case, what you'll get back is a 3-tuple. You'll get a dictionary with the estimated causal effect under models that have simulated violations of the counterfactual consistency outcome. You'll get an e-value, which represents how strong of an association there would need to be between a hidden confounder and the outcome to change your results, so kind of like getting after selection bias. And then the final thing you'll get is a matrix, which hopefully will be empty, and that matrix represents data points in your data set that have a predicted probability at or near 0 of being assigned to either treatment or control group. And so if you have an empty matrix here, that's good. That means you likely satisfy the positivity assumption. Okay, so we went through an example here of how we can estimate the expectation of tau I, this average treatment effect. But we might actually be more interested in individualized treatment effects, or conditional treatment effects, which we'll call the CATE here. So for example, we might be interested in estimating the effect of compensation to victims of violence in Afghan villages on future Taliban violence, not across the country as a whole, not an expectation, but maybe within individual villages, which vary a lot on things like ethnicity and language and geography. And so the data from this example that we're going to use comes from a recent study by Jason Lyle, who did just that using data from the U.S. Agency for International Development and event data from coalition forces in Afghanistan. And so again, a machine learning based approach is not the only way we could do this. What you could do, maybe if you want to look at heterogeneous treatment effects across, say, Pashtu versus non-Pashtu villages in Afghanistan, you could just subset those groups, estimate a linear regression for each of those groups. this would get really tedious really fast, especially like the more covariates you have, the more tedious this is going to get. And also in terms of statistical power, it's going to get really degraded really fast because you're going to be splitting the data up further and further, and you're going to be throwing away a lot of information. So it's really not ideal. But fortunately, we can use, among other things, a method called doubly robust estimation. And like double machine learning, we don't need to specify the functional form. And another benefit of doubly robust estimation too is that we specify multiple models here, and if we get the covariates correct for one of the two models, then we're going to have an unbiased estimate of the Kate. And so doubly robust estimation here uses, again, any ML models to predict treatments, predict outcomes conditional on the treatments, and then combines them into a final ML model to give you the Kate. And so once again, the workflow here is pretty much the same. We can instantiate a model, doubly robust learner here, pass in covariates, treatment, and outcome. And one thing to note here with these estimators is you can pass in either an array or arrays, or you can pass in any struct that implements the tables API, the tables interface. And so again, we call estimate causal effect, and here we get the Kate, and of course this is different than with estimating the ATE because these are individualized treatment effects, and so we get a vector of estimated treatment effects for each unit I, which in this case represents villages. And once again, we can get a summary of our model. It looks pretty similar to what we saw in the previous example, the one difference being the causal effect here is a vector rather than a scalar. And once again, by default, we don't have standard errors and p-values, but we can get them by setting the inference keyword argument to true. And again, we call validate. We can do those robustness checks and make sure that our model is robust to at least small violations of our modeling assumptions, or see at least that it's plausible that the assumptions here, counterfactual consistency, no selection bias or no hidden confounding, and positivity are met. And so what you saw in those two examples, that is a general workflow for all of the estimators in Causal Elm. So you instantiate a model depending on what type of estimation you want to do. You estimate causal effects using the estimate causal effect method. You can get a summary of your model using summarize, and you can also use the British spelling here if you prefer. And you would, of course, again, want to validate your modeling assumptions, which you can do with the validate method. And this applies across all of the models in Causal Elm. And so we've been talking about, at least in the case of double machine learning and doubly robust estimation in Causal Elm, they rely on some sort of machine learning model, right? And I didn't really specify what that was. I just said some machine learning model. But the Elm in Causal Elm is that machine learning model. It's the base model that Causal Elm relies on is an extreme learning machine. And the way an extreme learning machine works is it's a single layer neural network, but it does not use gradient descent. It actually uses randomized weights. And so what it does is it has this W matrix where the number of features correspond to the number of rows and the number of neurons are the number of columns. And those are all randomized. In this case, they come from a uniform distribution. Then we compute this hidden layer H by multiplying our inputs X by our weight matrix and applying G, which is an activation function on top of that hidden layer. And then now we have our output, our outcomes that we want to predict. And we have this nice matrix, and so we can easily get predictions by just solving the least squares problem. So we can get this vector beta by just multiplying y by the pseudo-inverse of h. And then to make predictions here, we just pass in our test covariates, multiply them by our weights, apply our activation function on top of that, and then multiply by our learned parameters beta. And actually, in causal elm, we don't just use one elm, but we use an ensemble of elms. This is good because it reduces variance, and it also enables us to get probabilistic outputs, since each individual elm is minimizing the least squares loss rather than, say, like cross entropy. You could, in theory, for an individual elm have predictions a little bit outside of the range of discrete variables, but by using an ensemble, we can get probabilistic predictions. And in this case, by ensemble, we use a bagging strategy similar to like if you were to use random forests. And then as far as activation functions, there's 13 different activation functions, and we usually don't think about activation functions providing regularization. You usually think of like maybe dropout or L1 or L2, but actually, depending on what activation function you use, it can provide a degree of regularization to your model. More aggressive activation functions, like say the binary step function, are going to give you more regularization than a smoother function, like say swish. And this actually can greatly improve performance of your estimators here. So on that note, if you do run causal elm and you get some estimate that looks pretty wonky, like you'll clearly be able to tell, don't panic. You're probably not wrong. Don't think you need to like run some cross-validation and do a bunch of fancy things. It's likely the case that you can just try a different activation function and you'll get good predictions. And so here I did mention, we went through a couple examples, but there's a bunch of different estimators here in causal elm. So for computing average effects, you can do interrupted time series estimation, and from that you can compute mean effects or cumulative effects. There's G computation if you're familiar with the biostatistics literature, and with G computation you can estimate both the average treatment effect or the average treatment effect of the treated, and of course double machine learning, which we went over. And for Kate estimators, besides doubly robust estimation, which we just talked about, you can also do S-learning, T-learning, X-learning, and R-learning. And okay, so what is the design principles here of causal elm, and how does it compare to other packages? So one of the big overarching things in causal elm is simplicity. So when using causal elm, there's no required imports. So if you've used something like econml in Python, or causal li, I think is Salesforce's maybe package in Python, they have a bunch of, you have to import other models. So they have these like classes that you can use as estimators, but for the machine learning models, you have to import like scikit-learn or stats models or something else, and then instantiate those models. That's not the case here. Another thing on that note is you only need to know really four functions: how to instantiate a model, estimate causal effect, summarize, and validate. And as far as inference goes, all of the models here use randomization inference, which is both a pro and a con. It takes a longer time to implement, but it's a pro in that like the p-values and the standard errors for all of the models all have the same interpretation. And one trade-off, of course, on that is that you do lose some flexibility. The estimator or the machine learning model here is based on extreme learning machines, so there's no like random forests or neural networks or anything else. So you do, in exchange for the simplicity, you lose a little bit of flexibility. It's also very interdisciplinary in its approach. So if you look at, again, a library like econml, most of the estimators implemented come from the literature on econometrics. In causal elm, there's kind of a smorgasbord of different ideas here. So like G computation and this idea of the E-value actually come from the epidemiology literature. A lot of these other estimators like double ML, doubly robust estimation, come from econometrics or more broadly from statistics. And the idea of randomization comes broadly, randomization inference or permutation-based inference comes more broadly from the statistics literature. So there's no like single favored discipline or favored approach here in causal Elm. And then finally, it's designed to be hopefully very lightweight. So part of that is, of course, being written in Julia, which makes things pretty quick. And also, causal Elm is implemented entirely in the Julia standard library. So there are no dependencies other than for testing, we use the data frames package. Okay, so first off, I hope at least someone in the room has watched Step Brothers before and gets this reference. But what is the way forward for causal Elm, but more broadly, I think causal machine learning with Julia? So in causal Elm, we're thinking about implementing maybe more sort of estimators and implementing the instrumental, in some cases implementing the instrumental variables version of some of these estimators like double ML, doubly robust estimation, and adding support for using GPUs, which I think should not take too much time, to be honest. But more broadly, I think there is a case to be made for developing an ecosystem in Julia for doing causal machine learning. So sort of building an interface package, sort of like the geospatial community's done, or like tables.jl, so that if somebody reads a paper on a new method for causal machine learning, thinks it's cool, they want to implement it in Julia, they can do that, implement their algorithm, make sure they implement our interface, and then somebody as a user could use a simple interface similar to what causal Elm does, and if they just know these 4 functions, say how to instantiate the model, estimate the causal effects, summarize and validate their model, they can use pretty much any estimator that they want to know. And so of course, always looking for contributions or feedback, so if anybody's interested, you can let me know after this talk, or I think the link to the repo or the docs is up here on the first slide too, so yeah, let me know. And that's the end of this presentation.
Thank you, Darren Colby.
Thank you.
Thank you for enriching the Julia community. Has anybody from the audience thought of questions at the moment?
So first of all, thank you, because that's a package I wished we had a few years ago. How do you think about which estimator to choose on the average treatment effect side? What are kind of your defaults and how you think about it when you're choosing which one to kind of start with?
Man, that's a really good question. Well, I think it depends a little bit like on the structure of your data, right? So like if you have, say, time varying confounders, G computation might be your go-to. If you have a lot of covariates and you probably don't know how they're all going to fit in like the functional form, I'd say probably like a double ML. But in general, I think it's very problem specific. Like it depends on the question you're trying to answer, the data set you have, and then like the assumptions you're making, which as of now, we don't have instrumental variables based estimators implemented, but we might in the future, especially depending on demand. So that would of course come into play. And then of course, depending on what you're trying to estimate, and also whether your data is of a time series nature or not, and how many units you have. So if you have like a single unit that's treated at some point and it's like sort of a before and after thing, then by default you're going to use interrupted time series estimation. So hopefully that answers your question.
Well, thanks for your talk. It was really interesting and all your work. If I would need to use a different model other than the extreme learning machines, would it be simple to plug a different model and use all the rest of the machinery there?
I mean, it's open source, so in theory you could, but in practice, like I said, one of the principles here is simplicity, so you do lose flexibility, and so I don't want to like say you should use causal elm in every possible scenario. So in that case, you might be better served by like econml in Python or something else. But that also gets to like what I just mentioned about maybe building out a general interface for causal ML so that someone like you who might be interested in using something else can have a single interface to estimate causal effects with whatever estimator you're interested in using.
Okay, thank you very much.
Let's give one more round of applause. Thank you again.
Thank you.
And now is the time for the break. Hope to see you in a little bit. Hello everyone, hope you took a comfortable seat and we are ready to start another block of 3 sessions this time. The first 10-minute session will revolve around Sol.jl framework for symbolic AI. Giovanni Pagliarini, a postdoc actually, and of course a Julia enthusiast, will present the developments in model symbolic learning. Please welcome Giovanni.
Thank you. I'm a postdoc at the University of Ferrara, and more specifically at the Applied Computational Logic and Artificial Intelligence Lab, where we are building this tool called Sole, a framework for symbolic AI. And I was last year at JuliaCon 2023. I presented the framework, and I went into formal details, and I presented the motivation for it. Today I'm just overviewing it and reporting some recent developments of it. So very briefly, Sole is an early stage framework for symbolic AI, also called good old-fashioned AI, which is mainly decision tree learning, rule extraction, and random forests and gradient boosted trees, all of those methods that are based on formal logic. Sole in particular focuses a lot on a knowledge representation in form of syntax trees. So the formulas that you can extract and represent within a decision tree are actually represented as logical formulas of some logical formalism. And the cool thing about Sole is that it separates the machine learning model level, the decision list, the classification rule, random forest, and the underlying logical language, which can be propositional logic, modal logic, or first order logic, and so on. We actually started this endeavor 3 years ago because we wanted to extend standard propositional decision trees in such a way that you could make them rely on more expressive logics, such as modal logics of time and space, and then you could basically learn formulas of any logical language. And this is how the modal decision trees package was born. Then the aim at generalization got out of hand, so we started delocalizing parts of this package into dedicated packages, and this is how the core of the Sole framework was born. The core packages of Sole are these 3. The first one is a symbolic engine where you can represent formulas of many different logical formalisms, propositional, modal, and first order ones. You can parse and generate, for example, randomly formulas, and you can apply minimization algorithms for simplify them. And most importantly, you can check the truth of these formulas onto pieces of data. When it comes to real data, then you can use the Sole data package for representing formulas that are based on concrete atoms, so that actually have a meaning. And these are formulas that you can actually check on data sets, like normal machine learning data sets, tabular and non-tabular, depending on the logical formalism, which is essentially what a decision tree does under the hood. But not only the decision tree, all of the, let's say, all of the rule-based models, so decision trees, random forests, gradient boosted trees, blah, blah, blah. So the Sole models package allows you to, once you've extracted a machine learning model and you have the decision tree in your hand, to investigate it, to extract rules from it, evaluate it, and also like prune it, merge different models, and play around with the knowledge in symbolic form. Around these 3 packages, we have been experimenting with algorithms that are sometimes closer to the data, for example, symbolic algorithms for feature selection. Of course, we are implementing a few learning algorithms. These are basically the most well-known algorithms, which are 30, sometimes 40 years old. So we're trying to rebrand them and give fresh implementation of them. And we find that Julia fit perfectly this role. And once you've trained the model, as I said, you can play around with the knowledge you've extracted. So we have been playing with minimization algorithms, and some things that you could do are, for example, you can check that the model satisfies some constraints. You can verify some property of the models. I've put other packages external to Sole, which may relate in some ways. One of them is the decision tree learning package, decisiontree.jl. And so last week I wrote this tiny package which simply converts decision tree learned via this package to Sole compliant models. And I wanted to give you an idea of what you can do with this tool. Sorry? Font size. So yeah. Sorry, I would have forgot to ask. So I hope this. Okay. So with the iris classification dataset. Okay. So 5 minutes. Okay. So with the iris classification dataset, I split the dataset into 80% training and 20% test. I train a decision tree using the standard package, and this is what I get. So in this tree, if you look at the leaves, it tells you that during training, 30 instances fell into that leaf, and out of those, 30 were actually of that class. So this tree basically overfit to the training data. If you look, all of the leaves correspond to high confidence rules. So now I can convert this model into a Sole model, and I can extract the rules. As I said, they are represented in as logical objects, and I can inspect the metrics for these rules. Sorry, I didn't expect this to happen. So with the last line, I've asked the framework to reduce the size of the rules, because sometimes you can apply some minimization algorithms. And something that is not evident here is that, I'm running out of time, so I will just tell you. There's a column here stating the confidence for these rules, and it is essentially 100% for all of them, and this is because these are the training confidences. But you cannot trust the training confidences, so next time I'm going to call this apply bang function, which is like a predict function, but it also changes the state of the model, so that then when I extract rules from it, I see the actual confidences on the test set. So one of the rules earlier it had a high 100% confidence. Now it has a 33% confidence, and then I can do other things, like I can join the rules for the same class into something that is essentially a DNF, and then I could apply some logical methods to study this knowledge. Okay, so. We have been the only user of this framework, but we're basically asking if anyone is interested in this tool and could find a use. We know that it's unique and that the code is mostly usable, although the documentation could use some refining. So if you are interested, we have a bunch of material, and if you want to know more or contribute, please reach out. Thank you.
Thank you, Giovanni. Anybody from the audience has any question on this expert?
It's mostly Boolean operators, and you get to choose what kinds of atoms you want. For example, you said atoms can be as simple as a simple thresholding, or if you look at the rightmost one, that's like linear combination of that's called a unique oblique atom, because it's multivariate. So you actually get to choose that, but you have to have a learning algorithm that extracts that kind of formulas. But we've designed also algorithms for extracting more than propositional formulas, like temporal formulas for time series or spatial for images.
Thank you very much for the talk. What other parts, the landscape of symbolics and logics is very broad, from, you mentioned higher order logics, description logics, whatnot. So what does logics actually cover, apart from decision trees and more sophisticated decision trees?
so it was built with machine learning in mind, like for representing formulas that you would extract with the decision tree, and then we generalized it. So I think I'm not sure I found something that would fit exactly what we were trying to do. I would say that the machine learning oriented view is the novelty. Let's say you can check out the documentation, and maybe we can talk later if you would like.
Let's give one round of applause.
Okay.
Thank you. Next, we have another PhD candidate and a Julia enthusiast, Wouter Nauten, who is about to share news on the Julia package GraphPPL.jl in the domain of probabilistic programming languages. GraphPPL uses Julia's metaprogramming functionality to transform high-level user code into correct Julia syntax. Welcome, Wouter. The floor is yours.
Now they can. Wow. Okay. Hello, my name is Wouter. I am a PhD student here at the University of Eindhoven, and I'm going to present to you what's new with GraphPPL.jl. So first, let's talk about what is GraphPPL.jl. I'm going to piggyback off of Bert's keynote this morning. GraphPPL is a probabilistic programming language used in the RxInfer Bayesian inference ecosystem. It is the front-end design-specific language for the RxInfer inference engine, and it is a language for specifying probabilistic graphical models. So the first thing we did with GraphPPL is that we made it completely inference backend agnostic. So the new version of GraphPPL completely does not depend on the RxInfer inference engine. You can specify your probabilistic generative model, and it will output a factor graph for you. So it will give you a factor graph representation of your model. In order to do this backend agnosticism, we implemented what we call a plugin system, which is basically just an extensibility system for backend developers. For example, RxInfer.jl, which does variational inference, uses a variational constraints plugin in which you can specify constraints on the variational posterior, which is then used by the inference backend to do Bayesian inference. So this gives us a very general, lightweight, but still customizable data structure with which we can represent probabilistic graphical models, and it can be used by any inference backend. So if we look at the syntax of GraphPPL, we can specify a generative model with the add model macro. Here I have a model that is written in the previous version of GraphPPL. So as you can see, we define a bunch of constants. We define x as a random variable, we define y as a data variable, and then we can specify a probabilistic relation with the tilde syntax. Now, in the new version of GraphPPL, we can actually infer whether or not something is constant, data, random, whatever. So all these lines at the top, they all go. I don't like them. Similarly, we have this x0 argument, which is presumably a probability distribution because we extract its mean and covariance and then pass it into a multivariate normal again. I also don't like that, so it goes. Also the parameter n, which is supposed to be the amount of data points, we can actually infer the amount of data points when we get data, right? We know it. So it also goes. So that means that the new syntax in GraphPPL for the same model in GraphPPL 4 is a lot shorter. So it does not contain all this boilerplate that we had previously. Another thing that we support now is nested model support, what we call nested model support. So as you can see, we have these two lines. Do you see? Can I? No, I don't have a cursor. But we have the S1 and Y1, which are being initiated as a Gaussian distribution, and then we have the same two Gaussians in our inside the for loop again. So we can take these two lines out. we can make a separate model. We call it submodel, include those 2 lines, and then use this submodel, this GraphQL model, inside a larger model. So we can use any GraphQL model as building blocks of larger GraphQL models. Now, in this example, it's obviously a bit overkill, right? But let's go crazy with this, all right? So you guys have all heard of neural nets. You all know that, hopefully, that a neuron, an artificial neuron, is just a dot product between a weight vector and an input. We add some bias, and we push it through an activation function. So here we have the GraphQL model for a single neuron. We instantiate a bunch of weights. We put a prior on it. We take a dot product. We add a bias, and we pass it through a ReLU. Then we can create a neural network layer by just copying this neuron n times. So we have still our in, our out, and n. We copy this neuron n times. And if we then want to make a multi-layer perceptron, we stack a bunch of neural network layers. So this is like 15 lines in total. And if you actually instantiate this model, you actually create 28 neurons, more than 300 factor nodes, with over 1,371, not over, exactly 1,371 connections in your factor graph. So you can spawn really big, complex models with a very simple syntax. So that's my talk. If you want to play with this, please check out RxInfer for a fully integrated example with an inference backend. So that's nice. You can run inference in your models. If you like the progress, give us a star on GitHub. That really supports us. And if you have any questions, I'll be happy to take them.
Thank you, Wouter. We have some extra time for questions indeed. Thank you for the simplification in the programming work environment. Anybody curious to learn more?
So which kind of deterministic operations are allowed in this model language?
Basically, so for the model language, you can put any deterministic operation. Actually, we leave it to the backend developers to determine whether or not something is deterministic or stochastic. For us, it's just, well, we create a factor node or not. However, if we have something that is labeled as a deterministic relation and all the arguments are known at compile time, we'll just compile it away. Like, we won't create any factor nodes because everything is known, right? We can just evaluate it and push it in. But we leave it to backend developers to say, well, this is deterministic, this is stochastic, and then it's up to backend developers to see how you handle this.
Maybe 2 or 3 more questions.
Thanks for the talk. Yeah, just a general question. What's next for GraphQL?
That is a very good question. I'd say, so my work will now mostly focus on the actual inference, right? So it kind of depends what features people will put in. So probably I would want to have more plugins. So sort of debugging plugins or a way in which you can plot your generative model, and it looks nice, so that you have more debugging functionality in GraphQL.
So this model language is then actually quite similar to the Turing model language, right?
It's very very similar.
Would there be a perspective that we maybe have one layer up so that we just have the model language, and then you decide compile this in a graph way or in a Turing way, and then we go to different inference engines so that we get to a common model language and then kind of different intermediate representations?
So this work is actually an attempt to do that, and with the graph as sort of the compile target. So, well, if I see the Turing guys around, their talk is after mine on the main stage. I'm going to go there. If they would want to do the work, they could adapt this as their language, and we would have this universal system. But yeah, it takes some work, right? Because it's a different language. But that's why we made it backend agnostic.
please help me with pronunciation, with your name. Dario. Let's say again. Dario. Dario. Yes. And Anas. In the last talk in this block, Daria and Anas tap into the challenges of tracking and debugging in machine learning model developments. They shed light on the application of CI/CD methodologies in the Julia ecosystem. Let us welcome the next presenters.
Testing. Is it working? All right, cool. Yeah, so great to be here. My name is Anas Abdul-Rahim. I am the team lead for AI at JuliaSim, which is a modeling and simulation platform that's tasked with building the next generation of tools to enable the next generation of technology that engineers can bring to our world today. Our talk today is about bringing modern CI/CD machine learning pipelines to Julia and making it more accessible to people in the open source community. From the JuliaSim perspective, whether it's trying to build, machine learning models from the JuliaSim AI perspective, whether it's trying to build machine learning models that will accelerate your inference time so that instead of a simulation running on a supercomputer taking, several months, you can try and scale that workflow down to a week within more manageable resources, or trying to discover, missing physics to a particular physical asset that you have in real life, which you have a simulation for, and you also have data for, and you'd like to kind of find the bridge between the two that actually properly represents the behavior of the deployed asset. Building these algorithms themselves require processes that allow you to, that will augment your ability to kind of develop it in a way in which you get outcomes that are expected and tempered and methodological. So the way I want to kind of start this off is through this comic from QCD, and the idea here is that most people, when they first deal with machine learning, the typical kind of exposure to the workflow is you have an API that's provided to you, you have a data set, you have a bunch of hyperparameters, and you kind of just stir the pot, so to speak, and you hope that at the end what you end up getting as a machine learning model is something that will meet the outcome or expectation of the kind of result you were looking for. And the idea here is that, in fact, when you look at machine learning from a production perspective, indeed, there are actual processes that lead to incredible results because of the fact that machine learning is a data-driven model process, is a data-driven model, and the actual process of building machine learning is a data-driven process. So every time you build, one version of a model, or I'd like to move away from the word model and move towards pipeline, you get insight on why it failed and what you need to do next in order for you to iterate and build something that's more robust and scales to the actual application here. And the idea here is that it turns out that within the Julia ecosystem, juicing and why it's required and needed, and then after that we'll be going into the latter half of the presentation, which Dario will be leading, which will be a demo of the actual workflow that is being proposed and the kind of tools that the open source community can use to help create pipelines in a more robust manner. So, most people here, I'm assuming, are very familiar with, a basic generic machine learning pipeline. But of course, for those who don't know, and just kind of a brief overview, you start off with generating a data set, whether it's collecting one from the internet, whether it's having a simulator and querying it. The next step is to pre-process it, put it in a place in which the machine learning model can deal with more appropriately based on how it's formulated. And then you choose your model architecture, you train the model, you validate it, and you kind of repeat this loop over and over and over again until you converge to something that gives you the results that you want. And obviously the last step is to deploy, and this is part of the kind of the continuous deployment aspect of things from the CI/CD acronym, but this is a part that we won't actually be discussing today. So moving on to like the motivating factors of why it's important to have these kinds of processes when it comes to developing machine learning algorithms. And the first thing that I'd like to motivate here is that machine learning is incredibly hard to debug. And the reason being is because when your code fails, when you run your test or you run something in Julia, you're going to have the REFL barf back at you and tell you exactly what it is just went wrong. And you're going to have the code trace to walk back and go back to that line of code that tells you this is the part in which you made an error for. That doesn't make sense. But when you have a machine learning algorithm, it'll just run and it'll just give you a result. And whether that result is correct or not is completely up to the metric that you have, or in this case, the kind of visual obviousness of this being wrong. So the example on the left here comes from OpenAI, and the source is at the bottom, and it's about faulty reward functions. And the idea here is that you have this video game called Coast Runner, where the task is, it's a race, you try and finish the race and you try and collect as many points as possible. And so the kind of rational thing is, well, if I design a reward function that's supposed to motivate some kind of behavior for my agent to accomplish the task of finishing the race and collecting as many points as possible, the idea here is, well, if you just create a reward function that says, try and collect as many rewards as possible, then what it ends up doing is it realizes, well, and in that reward function, the game itself doesn't reward you for finishing the game or progressing through the race. It just rewards you when you get points. So if your reward function only rewards you whenever you gain points, then the agent kind of finds this clever solution where if I just do a donut in circles and keep collecting the same point over and over and over again, then I'll never finish the race, but I'll meet the objective of maximizing my reward. So you end up getting the most rewards you can possibly get in the game, but never actually meeting the objective to begin with, which was to actually finish the game from the get-go. And these are the kind of pathological behaviors that kind of come up. And this is just one example. For example, another example could be when you're doing classification and suddenly, every single image you feed in turns into a cat, and you're just wondering, why is that the actual case? And again, there's no error that was thrown. You did your forward pass, you got an answer, but there's no way to actually debug that process. So the idea here, and this is really the overall theme that I'd like to kind of bring up here, is that machine learning is software and you should treat it as such. There are very strong design patterns that exist in the software development community that need to be directly applied when it comes to actually building machine learning as well, including pipelines. And the idea that I want to kind of first start off with here is that it is so important to actually treat the development of a machine learning pipeline through the same lens as you would developing software when it comes to the ideas of test-driven development. And of course, many times we'll start off and use a package, and the API of that package has been thoroughly tested. But then when you use it in your own context, in however way you do, there are always subtleties and nuances that comes into play here. An example could be how you normalize, for example, or when you initialize your neural network and its distribution of weights results in activations that saturate and don't let you train well or whatever it may be. These are all things that you can fundamentally test. And the important thing here is that, as will be shown later, that you can actually structure your machine learning project in a way that it turns into a package, and you can kind of use the testing ecosystem of Julia to actually create this pipeline in a test-driven manner. I should probably put my phone out just in case, just to make sure we're on time here. Okay, cool. In terms of here, these are just examples of the kind of tests that you can do. So if you have a simulator, for example, you can test your actual simulator if you're building one from scratch, or if you're just kind of evolving your system. You can test the distribution of your data, test normalization. There's so many parts of the pipeline that you can test. For example, when you train your model, you can pick a baseline that the model should succeed in order for you to move over for your next step. And these are the kind of tests that you can create along the process before you move on to your real task, in order for you to actually have a pipeline that when you get to the real task itself, you're not losing your hair, so to speak, which I have very little of, to trying to accomplish your goal itself. So this is an example where, as you can see, the way the project is structured, and Dario will be going through this. So I just realized, already 10 minutes in, I'm trying to leave as much time for the demo as possible here. But you can see that the way you structure your packages, you have some kind of template that you're interested in, like a broad generic machine learning pipeline that has, your data generation script, your layer, which here is your actual model, your pre-processing, your actual training algorithm, and then here you can see that in the test set, in your run test file, that you're running all your tests that include each part of the pipeline that you would typically run together, and then only after then you run your actual experiment, the thing you're trying to conduct and get a whole final outcome for that's hopefully useful. And the idea here is that if you follow this mentality of treating package development, of taking the tools of package development itself and applying it to your machine learning project, you get tons of benefits. So one of the key things that is absolutely hair-tearing is the notion of state. So when you're evaluating from a REPL and you're just running a line of code, and you can notice sometimes that suddenly you'll get a different result, and you won't know why. But then you'll realize that maybe 10 line executions ago, you did something that overridden a state inside of yourself, inside of your REPL, which you don't know about. So whenever you kind of instead push all your evaluation of your machine learning experiment / pipeline to the testing environment where you just run tests and it runs all the tests and then it runs your actual experiment, you get a sandbox state. So you don't have a sense of, you don't have to worry about this fact of that you might have some kind of hidden state that you evaluated earlier. It's all fresh. It's basically starting a REPL from the start in some sense. So the next thing I want to get to very quickly here is the idea of reproducibility. And this is such an important part. So this is an example, again, from OpenAI. They always have the cool stuff, which is hide-and-seek game, where on one side, the whole point is they have to learn to kind of win the game itself, which means they don't get caught by the opposing team. And on one side, you have, they learn to kind of block the passage so they can't get in. But then later on, the agents realize they can take the map, so the ramp, and actually climb in and lose the game. And then there's this other version of it, down the line in your pipeline, where they learn to pull in the ramp first before they block the passageways, and that way they win the actual game. And so this is more illustrative, but the idea here is, suppose you had an algorithm that suddenly made a leap in performance. How the heck did that happen? Right? To be able to kind of track exactly what kind of code state got executed in order to get this kind of performance is very, very important. And so the next thing, of course, that I want to bring up is the idea of using Git in order for you to be able to track the code changes that went into both the development of the tests and also the actual code state and hyperparameters and everything else that went into the experiment that you just run as well. And this gives you a history of what exactly has gone into the experiment so far, and it even gives you the ability to move down the line of comparing different code states so that you can know again, have an understanding of how the project has been developing, what led to what, and getting insights from that as well. Okay, and again, kind of rushing through this to make more time for the demo. The idea of the kind of workflow that you would go through is you write your individual models, you write your tests, and it's exactly like you develop a package. You go back and commit what you need to write for your test itself, and then when you run your actual experiment, you have one final commit that designates that this commit is for the experiment that was run. And then when you look back through your Git history, you'll have a very readable kind of chronological timeline of what exactly went into the experiment up to that point. Okay, and the idea here is that you can go back and look at Git diffs and things like that. So the next thing I want to talk about is that the reason why you also need these kinds of pipelines itself is that machine learning has a lot of knobs to turn, and being able to kind of keep track of, in order for you to explore this entire space, you need a lot of compute, or you need to be able to run things in parallel. And one of the interesting things that you can do, one of the interesting ways of kind of facilitating this is the idea of being able to kind of hook on these runners that can run multiple things in parallel for you, and being able to kind of like scroll through it. And something very familiar for people in the Julia ecosystem is when you finish developing a package and you push your tests, you have a build kite runner that runs all your tests for you. And then we just showed that your experiment, if you kind of hijack this process of test-driven development and using the Julia package ecosystem, you can now push all your experiments in the same direction as you would when you push a test to a repo. So it's the same kind of mentality here. And this will allow you to run multiple things in parallel as well, and being able to kind of explore your space as needed. Now, of course, I'm not suggesting for people to suddenly hijack the open source community CI and start running, machine learning experiments and block everyone's progress for that. I'm just suggesting that, when you create your pipeline, the same way you think about how your package gets developed and run in the Julia ecosystem, you can now hijack these processes for your own use with your own compute. That's probably one thing I want to mention. Okay, and yeah, this is just going through this very quickly about how you can. How it makes it much more easier to take a runner workflow, just like you conveniently think about in your package development, and run multiple runs in parallel, explore them, and then obviously the last piece to all of this is first you start off with a sandbox environment that will run everything and test, then you will commit everything so you can make sure you have a history of what you're doing, and now you want to be able to explore in parallel very quickly. And the final step to all this is being able to keep track of all your explorations. Like I mentioned earlier, the idea of developing a machine learning pipeline is that deep learning models are data-driven algorithms, and the workflow behind making them succeed are data-driven processes. The idea of running an experiment, what happened, why did it fail, working back from that information, iterating forward, and being able to track all those efforts is incredibly important. Now, of course, if you're really into torture, you can go ahead and pull out an Excel sheet, and best of luck. But of course, the most beautiful thing is, again, machine learning is software, treat it as such, and one of the strong design patterns when it comes to software development is integration of tools. It's very important to not start from scratch every single time, and having some kind of experiment tracker to collect all your results that you've been working on so far, so you can have some kind of history of what it is exactly that you've done so far. And for example, this is what's called a parallel coordinate plot, where every vertical axis is a parameter that you've done, and if you trace through it, it would be one experiment. So, you know, I used a dimension size of 32, and I used the dropout of this number. And you can kind of track all your experiments to see what ends up giving you the best kind of result. And the idea here is that, again, if you incorporate these kind of experiment trackers into your actual workflow, and then you have this kind of final completed pipeline that will allow you to develop machine learning algorithms in a way that will not only give you the opportunity to develop something that will be very robust, but at the same time, it'll give you the kind of insight and accelerate your ability of an iterative workflow. Because when it comes to data-driven processes and learning how to actually, you know, take your algorithm from something that's failing to something that's giving you state-of-the-art results, there's so much that goes into it, and keeping track of all the details along the way so that you can go back and reflect and do your post-analysis is going to be key here. So now what I'd like to do is kind of hand it over to Daria here, who's going to talk about you know, an example of how in the Julia ecosystem you can use the tools that already exist to create this pipeline and then demonstrate for you actually what that all looks like. So I'd like to hand over to Daria.
Thank you. So as Anis basically spoke about right now, we used a bunch of tooling to actually come up with a pipeline. And the important thing to note here is that these pieces basically are put together, but they're completely independent of each other. What that basically means is that you can swap it out, swap each part out independently of what it is that you actually want to do. What we did was we took over the Julia PKG ecosystem, the testing environment, and CI, and then hooked it up all together to basically give us this very extensible pipeline that we can use to run our experiments and pipelines in parallel and keep track of them properly. So now I wanted to go over and show you what an experiment or a pipeline package would look like. So let me make it a little bit bigger. So hopefully this is something very familiar to everyone here, right? So this is basically what a Julia package looks like. We have our source and test directories and everything exactly like we would set up anyway. What is slightly interesting is this lib directory. Now here is where we store something that we call template experiments or template pipelines. What they are basically is something you know, very, very simple that we would want to replicate over multiple of our pipelines and experiments. It has a file structure that we will explore in a minute, and it has you know, existing sort of context and pieces that basically make it easier for the next person who is trying to come up to start with the pipeline directly rather than having to futz around with Julia. But let's now try and see if I can. Is this big enough for everyone? Hopefully.
Is this going to be a public repo? Because right now it's private. Yeah, I mean, yeah, it still hasn't been released, but yeah,
it hasn't been released
yet.
yet.
Not yet.
But this.
Yeah, we'll do some touch-ups, and yeah, we have an agenda for that.
Right. So I've basically loaded in the same package that you saw earlier, and what I want to do is I want to start with creating a new pipeline using my templates that I have, right? So here is something like we're already familiar with. We are used to forking experiments, right? So we have the template experiment already that we want to basically now use. So all I have to do is call this fork experiment function. It'll start a new project for me. It'll and hopefully also activate the environment. As you can see right now, it's completely empty. So that's cool, right? What that did for us was basically give us a new environment where we can actually implement our pipelines. So I'm going to exit the REPL really quickly, and I'm going to come here and show you a pipeline that I was working on earlier for this demo. Now, again here, as you can see, this is again just a simple Julia package, right? And now let's go and explore some of the other things that we have access to here. All right, let me switch back to our GitHub repo. So this is exactly the same thing, just the same package. And what I want to point out here is specifically the same notion that we saw earlier. ML is software, so we should treat it as such. This is just a package, and with ML, we saw that we have these generic design patterns that come up over and over again. Your basic steps of data generation, of pre-processing, training, visualization, such and so forth, right? So we can see all of those things represented here as well. So let's go into one of these things. We see all of those files right here: data generation, pre-processing, modeling, etc. Okay. Here we have very, very simple functionality that we'll talk about in a minute. But the idea here is that we have these compartmentalized functions which consume some parameters and then output certain output variables that are necessary for our pipeline to basically come together. The same things that we see here in the source are also replicated in test, right? So you have your data generation, your modeling, your pre-processing, and so on. Now, while we are in the test environment, I want to quickly go over to the run test script. As you can see, again, something like we're very, very used to, right? In package development, we have all of our test dependencies, we load all of them, and then we start running our tests. This is something very standard. What we've added on top of it is the idea of an experiment, right? So this is where we will actually be doing our experiment running. So let's now look at what this run experiment script does for us. All right. So we can see what we have here is a workflow function. So this is the function that we will be using to actually execute the pipeline that we intend to track and actually make use of in our downstream tasks. As you can see, again, we see the replication of our steps in order, right? We have our modeling, we have the data generation, pre-processing, training, and so on. Interestingly, also we see that we add a bunch of logging for just logging our metrics as we go along for visualization, and finally we add some visualization to basically wrap up and see how we actually performed overall. So in this case, what we have done is we have taken over or sort of forked or built upon the MLflow client library. So this is an ML ops backend, which we have integrated alongside LabTracker. And its job is basically to help us both log and track all of our experimentation and do post hoc analysis for us. All right. Finally, we just have a run from config function. We will go into the config in a minute, but the idea here is that we should be able to now run all of our experimentation in parallel, as we spoke about. Right. So let's go to the config really quickly. This is a very, very self-explanatory thing, but it's very important for us to note that all the pieces that are required for our pipelines to run are present in there in very very organized manner. So, for example, we start with the port that our logging server is going to run on, something very simple. The module that we're logging, stuff like that. Again, so let's go into the parameters section. We can see here again that the same notion of this hierarchical component and sequential component that we have built is represented here. Again, we have inside our parameters the modeling component, the data set component, the train component, and so on. One interesting thing is that because of the way it is architected, right, it is all going to be hooked through CI, as we spoke about. It means that we can basically use any kind of data source. Anas mentioned using simulators or local files that we're loading, whatever the case may be. We can hook it up to cloud providers if the need arises, and so on and so forth. In fact, all of our compute runners could easily be something that we run locally with the help of CI local runners, or something built on top of cloud providers, depending on the kind of compute infrastructure needs that come up for your problems. Awesome. So with this, what I want to do, I want to run a quick experiment. Let's look at our config script really quickly. The same things that we saw on Git are replicated here, right? Let's say I wanted to add noise to my model and see how that performs. Or rather, let's see if I change the number of batches that come through, right? So let's do that really quickly. Let's say I want 20 batches instead of 10. Sure. What we'll do is we'll call the test function like we do in Julia always. So as a package, this will run off all of our tests, and we should basically see the output in just a moment. So what has happened there is our run experiment script is designed such that it comes after all of the PKG tests go through, right? So that means that anytime we see any kind of breakage, it will shout at us if something goes wrong. So we're just going to wait around, right? And this is what we are basically greeted with. As you can see, what has happened here is that it has told us that it has found the ability to run 6 independent runs based on the config that we have, and it is giving us the basic what's it called, the URLs to access any one of them. So what we can do is we can go over here, and this will take us to our MLOps backend. Soon enough, this will load. Let's just go to the experiment tab for now. Awesome. So here you can see all the runs that I had run previously. These are basically instantiations of our pipeline over different configurations, parameter structures, so on and so forth. As you can see, we have a very clear view of all the things that we can indeed check for example, any columns that we might want to add. For example, I don't want to see what dataset I was running, but I do want to see the loss that my model is at currently. So this is all happening in real time, right? So any time my model updates, all of these values will get updated. So we can go to one of these previous runs if we want and see what that looks like as well. As you can see, all of the parameters that we ran our configuration with are exactly replicated here. Alongside, we have metrics. So this is a loss metric that I wrote for my training script. And we can see that that plotted in real time as well, hopefully soon. All right, you can see, I mean, sure, this is doing something kind of nonsensical, but the idea here is that we can go into our model and analyze as it's running and even after the fact. As a matter of fact, what we can do again is we can go back to our experiment tab and we can compare across runs. Right, so we get this parallel coordinate plot again. Running over multiple experiments, we can basically see how exactly our progress has been, what caused our models to perform well, and what caused them to perform not so well. I'm a little bit short on time, so I will try to be a little bit quick here. But the idea here is, again, let's just go to one of our runs. We can see that what we have here is our commit URL. Well, let's go and see what happens here, right? It takes us directly to our GitHub repo that we were playing with in the first place. So we can see what actually caused the change in our model output, right? So in this case, we can see that we changed the width and height of the model that we were running with, and we changed the detection threshold that it operates with. This way, what we have basically done is we've come full circle, right? We started with a commit. That commit was replicated on Git, which then comes up on our MLflow backend, where we can actually do any kind of analysis and comparative work, comparative study that we're interested in.
Yeah. So yeah, that we're a little short on time here. We're trying to leave some time for questions. We were hoping a little more time for questions, but that puts us at the end of our presentation. And yeah, I think we'll open it up for questions. I know
Let's thank the speakers. Yes.
Yeah, thank you so much. That is super awesome, and I was totally trying to set something like this up myself, and it's not super easy. So I would love if there's as much as possible to kind of copy from this, especially also with respect to if you need like GPU devices. Obviously, you don't get them so easily from GitHub. How to kind of set up your own GPU devices. I saw that I guess you have their own cluster and how to hook that up. Mm-hmm. One question I have is, does it mean now that every time I push new Git commits, it kind of reruns all the experiments I have, even if they may be expensive and takes like an hour or something?
So that's a very good point, and I can actually demonstrate that here really quickly. So say I wanted to actually change my experiment. I want to do something interesting with it, right? So, hello?
I think you're just going to have to illustrate the point.
Yep, seems like the REPL is right. Let's say I wanted to change something in my config, and I rerun the experiments, and well, what that will do is it will spawn more runners, obviously. Now, this is CI, so we can choose what we want to happen here. We can have it fail fast for us, and because this is test driven, and we know that our tests are going to run before our experiments, if there is anything indeed that is wrong with the setup in our experiments, it will error before it ever reaches the point of ever submitting an experiment. What that means is that our CI and our experimentation queue and the analysis area, that our MLOps platform is not really going to get runs that are never going to complete. Or in the odd chance that it does, we can obviously clean up. But we have taken mitigation precautions to make sure that that we just don't get to that stage where we have to come back and clean those runs up.
Yeah, thanks for the talk. What is the connection, comparison, differences with Dr. Watson? Because that's one of the main packages that exist in the Julia ecosystem for this.
So Dr. Watson is obviously a very great platform, right? It allows us to orchestrate a lot of these similar, what do you call, pipeline pieces. What is different here is that we're able to basically, rather than having to track things manually via Git, what we are doing in this case is that we're offloading that work from the user to the experimentation queue. This way, we are not making manual Git changes, but we're letting it decide for us. As you saw in the commit messages, we're letting it basically figure out where those commits will end up, what experiments they're going to go with, and any other binary dependencies that those experiments have. So while Dr. Watson is really, really good for experimentation setup, and I recommend it, this is just a simpler way of making sure that the pipelining pieces are offloaded as much as it can be from sort of manual configuration and more to the compute.
Thank you very much for the speakers, and thank you, the audience, for attending. This is the end of the block, and you can go and enjoy lunch and come back for more sessions. Enjoy the day.
On. Yes. Oh, a little bit of distance. There we go. There we go. Let's just check what time are we at. Okay, we have 4 more minutes, so let's wait a little bit so that nobody misses it. We are 2 minutes early, but should be fine.
We're 2 minutes.
Right.
I mean, if you want to wait 2 minutes, that's fine. I think it's just lunch. We let people arrive.
Yeah. Okay, let's wait 1 more minute. Stand on this side. All right, I think we can start now. So welcome to this afternoon track. This, for the final stint. I hope everyone is still fresh and ready to take in these final set of talks. We have now Romain with designing satellite constellations with Julia. So kick it away.
Thank you. So this is a little talk presenting the work we've done at Eutelsat OneWeb, which is a company that designs and operates satellite constellations. So it's not small constellations like GPS or Galileo, etc. It's like these sort of mega constellations like Starlink or like with hundreds of satellites. The aim of this talk is to just present to you a general concept for a simulation tool we've built, because obviously we cannot really share like specifics or like actual data from simulations. But really to explain like what our approach was, and also to create the talk that I would have wanted to see before I started developing this, which means that I would really like to get general, just give general advice on like how we proceeded and how we attacked the problem of building a tool to simulate this in an industrial setting. So anyways, why am I giving this talk? It's also to show these cool animations. Thank you to our intern who built this, by the way. This is a quick overview of what these kinds of systems are like. So you can see on this slide that, you can see on this slide that we basically have a few satellites flying around, and these little hexagons lighting up and down are our users, depending on who they're served by. We change the color of the cell. All all this is to say that we have this problem where we really would like to simulate all these satellites interacting with each other, as well as all the components on the ground segment, and try to do this in a sort of relatively performant and efficient way that's kind of easy for people to use. So before we get started, I will just give a quick overview of what our business is, what we do day to day, etc., just to give you guys a bit of context, and then I will start to cover the technical details of the architecture of this tool. And finally, I will just give some general pointers on like what we found easy and what we didn't find easy in switching to Julia for this sort of development. Okay, so I work at the system engineering team at Eutelsat Group, and more specifically, I work in the OneWeb division, which is in charge of low Earth orbit satellite internet constellations. A couple of pictures just to quickly give you a bit of context. We have our satellites from the very last launch we've done last year. They're all integrated and folded up on the rocket, ready for launch. A quick commemorative patch from our very first launch, which dates more or less the mission of the company when it was created, which is to bridge the digital divide. That means bringing internet connection to people that do not have it, or where it's not available. So you have to think about like if you live on a boat, if you're a boat, if you're an airplane, or even if you are in some village that's too far away from the main internet backbone. This was the application case for our system. It's also not just low Earth orbit satellites. You can put as many satellites as you want in orbit. It's not really going to help you if you don't have the ground infrastructure to follow up. So just to give a bit of illustration, here's our antennas located either somewhere in Canada or somewhere above the Arctic Circle. These guys live on the ground, receive signals from satellites, and relay them back to wherever the satellites want the data to go. Finally, what does it mean to be a satellite constellation operator and integrator? It means that we have to do basically 4 things. Step 1, we have to design our constellations, get them working, try to get something that actually works on paper, and then find subcontractors that will actually build the components for us. And that goes from the satellites. So we go see Airbus and we might ask them to build them our satellite, something like this. Or maybe we will ask some software consultancy to help us to build some software, or we might even build it ourselves. Then once we have all the components set up, we would actually try to design the management element of the system. So software that would help all the components talk to each other, and just general integration of making sure everything works. In theory, that's where we add value, by putting all these components together. Finally, we operate the system day to day. That's what it does mean to be an operator. So reacting to all the problems that can occur in the air or on the ground, optimizing, reacting to random geopolitical events or natural catastrophes where you suddenly need to give service to a given area. That's the operation system. And finally, we have to sell our service because it's not free to launch these things. You're talking about multiple billion euros just to get satellites in orbit. So that's a quite important engineering activity that we have to do. Why am I listing all this? Is because at all of these steps, we do have to rely quite a lot on simulation. So if we're changing something or if we're designing something, we have to have confidence that it works. And if we're even selling or operating, we do not want sudden changes or unexpected changes to break promises we have made to previous customers. So this is how we end up arriving at we need to build these tools to really help us just do our job. These simulators exist for this. This is the final intro slide. We're actually going to get into the work of what is a satellite constellation now. In the team that I work for, the systems team, we have a sort of specialized modeling unit where our job is more or less to answer any question that can occur. And this is really the motivation. This is going to set the core requirements for this tool that we have built. People might come and say, okay, what's going to happen tomorrow? What is going to be the performance tomorrow? Or they might say something a bit more complex. What's going to happen if we open a new ground station antenna in this stadium today? Is it going to improve performance, make it worse? How do we integrate it, etc.? So we really need to be able to quickly return analysis on these sort of problems. Something we have found out is there's basically no way around building a full end-to-end system simulator. So being able to load the entire system, having all the chunks available for us to simulate, and then just making a quick change, running the simulation again, and also, I will go into more detail about this just after this, but also a way to simplify the simulations just to simulate only what we need so the result comes out quickly. Okay, so now I've explained to you that we actually really want to build this tool. What are the difficulties that we are going to face, and how should we architect this whole tool around it? Step one, when you build this kind of system, there's 100,000 components. And like, when we say 100,000 components, it doesn't really mean 100,000 variables. It means 100,000 full models of, for example, a terminal antenna or a satellite or something like this. Of course, there's like a lot of simplifying assumptions inside those models, but in the end, you need to orchestrate all these models together, just attach them, see if they work together, see if you're able to manage them in an efficient way, and then output your result. So okay, but like that's just a big thing. We could just throw a lot of compute power at it, and it would probably be fine. But the second problem is that, or maybe we could make like some sort of like simplified assumption, like grouping terminals together or something like that. The second problem we have is that our system changes all the time. So we need to simulate at quite fine resolutions, and we cannot really make like sort of statistical assumptions. Just as an example, and that's something that maybe don't realize about the systems, is that your whole system configuration tends to change every 10 seconds. So if I put an antenna out here today, your data path will be changing more or less every 10 seconds, which is like quite often. But now you have to multiply this by the number of antennas you have on the ground when you're doing a simulation. Same story, you're changing satellites 130 seconds, you might change ground antenna quite regularly, etc., etc. Another core requirement we have is that sometimes we need to build really long simulations because regulatory agencies require us to demonstrate that over an entire year we're not putting too much radio noise in the atmosphere, etc. So sometimes like the simulations are complex, they change all the time, and now we also have to build this whole really complicated system. Now we have to run them for a long time as well and also post-process all this data. The final problem we usually face with this, and that's actually what really drove us to develop a new tool, because we had an existing tool previously, but we really wanted to develop this tool because we want to be able to integrate really, really fine-grained modeling to say something along the lines of, if you have some sort of hardware failure in one satellite, you want to include this without breaking the whole simulation. And our previous tools didn't really allow us to do this easily. Anyways, so I'm going to change direction for a quick second, and I'm just going to go over what is a sort of like satellite communication system, just to give you an understanding of roughly what we are actually simulating. So there's basically 4 components. There's so from left to right, the user, which is not really a component of the system, that's just our client. We have our communications antenna, the satellite, the ground antenna, and then some sort of point of presence, which is basically the point where you're going to appear to the main internet. Simulating every single one of these components is really not that difficult. Like the satellite just follows orbital dynamics, and honestly, like this is not a problem where we care about exactly where it is. It's a problem where we care roughly where it is. The links themselves, it's not very complicated. Like it's just like there's a whole theory of how you would simulate how much data goes through a link depending on the gains, etc. But that's not hard. The really difficult part about the systems is to get them all to work together, and it's all the management systems around it. One thing we really care about in these simulations is to say, okay, like we don't want too many antennas to attach themselves to a satellite and then cause some resources to run out, for example, the power of the satellite to run out or something like this. So here this is an overview of what we actually tend to simulate in our current system. So this is a representation of a sort of transparent system. So we run the simulation only on the raw bytes that, or only on the raw bits that will go through the system, and it's just about the quantity of bits that we can go through. In the end, when you do like really high-level system simulations, you don't actually really care which path the packet will actually take. You only really care about what the end outcome is going to be. So what you end up simulating is saying, okay, like this antenna is linked to this thing. This satellite is linked to this other antenna. The whole path takes roughly gives you X amounts of bits per second, and then the connection between the antenna and the points of interface with the main internet just takes some amount of latency that's determined by the network topology. Already this is not very detailed, but it's already quite a significant challenge to achieve this like at a scale big enough to derive insights of the whole system. it can suddenly get more complicated, and this is the use case that we wanted to address in our simulator, is to say, okay, like sometimes maybe you're going to have multiple satellites in a row, and you might put something along the lines. Maybe like the satellite will suddenly start to read the packets, bring them up one layer, so the data will actually arrive. They will make some decision about where this data actually goes. And this is something we may not want to support in our initial tool right now, but we need to have the capability in our framework to be able to have this sort of simulation. Right. So we finally get to it. I think I'm going to take 2 seconds to drink a bit of water. We have built this tool with the goal of replacing an old MATLAB tool, and I'd just like to take a couple seconds to go over the design of this old tool, demonstrate that there are other solutions to do this, but we have decided not to follow them for a few, just to get more flexibility. So the way we used to solve this before was to first of all solve the problem in layers. So first of all, solve where the satellite is going to be. This is just orbital mechanics. You're going to just save this for all times of the simulation, move to the next step where you're going to solve the spacecraft schedule from the scheduler of this general system, and then finally move to terminal state, which then will give you the user experience for our clients. The really big advantage of this is that you have access to all information about all times, as long as it's been computed at the step before you're running. As long as it's been computed at a step before you're running. So, if you're calculating the terminal states, if you want to look at the position of the satellite at the end of the simulation, you're going to be able to do that. One big problem is that this costs enormous amounts of performance. Like you have to store all this data. And it's really not worth it as you make your simulations go bigger and bigger. So finally, our design goals were to say, we would really like to build a tool that allows the three following things. Step 1, we really want any systems to coexist. You want to put multiple kinds of constellations in the same simulation and have them interact. We have to support this. Finally, we want obviously to improve performance, because when we were running this, we're basically buying the biggest simulation machines that you can have on AWS, which is not the really cost-efficient way of running a simulation business. And finally, switching to Julia. In switching to Julia, we really aim to improve the modularity and general quality, so the general confidence we have in the result that comes out of our code. The simulation approach we chose to go for is to say we're going to split the problem into 2. We're going to allow people that write models to live their life by themselves and just write the models that they like. Just in complete isolation, which is nice. It allows you to build your own model, test it by itself, and then just move on with your life. And on the other side, we want people that manage the general performance of the simulation and all the data flows to be able to just do this on their own side without having to worry what the model is about. So in the end, we basically end up saying, if you're a model writer, you are allowed to create entities, just general entities that have some state, and you're also allowed to create ways to update these entities. This is sort of a entity component system, but simplified because there's no components available. You might say, okay, I'm building a satellite model, what kind of state does the satellite have? So maybe it has a payload, has a battery level, and maybe it has a position. Then you just tell us how to update these things, and we give this to the core team that will find a way to do it. This works quite well in the end in terms of performance, because Julia is able to just dispatch the right code that's already precompiled and everything. So you only have a small compilation hit at the first step. You may have a bit of dispatch that goes on, but in the end we find that it works quite well. We also and then to allow people who don't want to write models themselves but just want to interact with simulations, we also offer an additional interface that you can stop the simulation at every step, do whatever you want to it, and then let it keep going with its flow. In the end, this simplified design ends up being visible. This is how you use the simulation in our minds, in our idealized world of the first layer of the design. Just tell it when it starts, how long it lasts, how it will step. You will register a little entity, a Gen 1 satellite, which some initial state of your choosing, and then you will just push it forward, interacting with it if you need In our full solution, we find that this doesn't really work quite well, because if you have to insert 100,000 entities every time you create a simulation, that's not really going to work. So we ended up building like a little bit of niceties around it, so a sort of simulation templating system, as well as some sort of logging system to be able to save all the data. If we don't have these systems, you end up running into the problem that the simulation runs super fast, but you never have access to what happened in the past. You get only the final state of the simulation, which is not very helpful. One special solution we also found for this is to provide like standardized probing mechanisms which allow the users to just save some statistics about some variables as the simulation goes forward. So in the end, this is the final interface we provide to our users. You'll notice that it has changed a little bit from the previous idealized slide, which was more or less the idealized slide was more or less what we had on our spec when we started writing, and the final slide is what I did today to generate you this animation you saw in the morning at the start of the presentation. One thing that I will give is that after you've just provided the start, end, and step, we provide straight away a sort of templating system that allows you to state where the satellite are going to be positioned, and this one is called Walker Star because it's a standardized constellation configuration. But as a model writer, you're free to write any sort of templating system you like, and it will just go and instantiate your entities, and your simulation will just keep going. We of course maintain like the interface for just registering any random model at any point in the simulation, even midway through running, and then at the end you just run it, recover your results in your log file, and you get the same kind of thing. In the end, this plot is just exactly the same simulation I showed at the start, just focused on a different area. But here, now that you have the context, you probably understand a bit better what is happening. We have saved all the state that we required for our logging system, and you can see all the different entities flying through the simulation, some entities in charge of managing the resources of the others, and at the end, you get some sort of allocation, some sort of like resource allocation visualization of your simulation. While I have you seated down in front of me, I think I will just like put on the full system diagram of this. But this is when we transition into the main. This is when we transition into the actual how do we actually build this as a company, and how do we organize the code development process. So I've put like vertical line in the places where we separate our domains, but we basically start with 3 main domains. We have our library domain, which includes the really good libraries from the open source system that we more or less verify function correctly. And also our own libraries, which include specialized geometry primitives that are really like super specialized to our own use case, or some regulations data, radio frequency models, etc. In the middle, I've put what I've shown you already in the grade because you've seen it before, but some place I would really like to talk about is this big vertical line in the middle. The point of this line is to state that we are actually going to split the development process into 2. We allow the whole orchestration framework plus like the core models of the system to exist in a place where everything is tested, and the test environments are the development rules are very strict. And on the other side, it's basically the playground where you do your analysis. You write any random .jl script, start up a simulation, stop it in the middle, write your models that don't work or that do work, import any dependency that you like, and this allows us to really split the development system. 5 more minutes? Okay. And yeah, so we allow people to basically play around with the simulation, and it's really meant to be easy for people to use. That's why we spent a lot of time developing the API as well as letting people play around on the site. That's how it works. This is a slide that was basically missing from every single presentation I've seen in JuliaCon before, so I will just state our test pipeline. As an aerospace engineer, I cannot have a meeting without talking about how we test things or something like this. I think it's required by the Aerospace Guild. But one main problem that we have is that when you write modeling code, quite a lot of your models just end up sleeping for a very, very long time. You may design something, solve it completely, and then never use it again because design is finished. The problem is that maybe somebody in 2 years is going to wake up and actually ask you to rerun this analysis. So we actually try to run quite a comprehensive test suite to make sure all our analysis is able to rerun at any point in time. We obviously have our integration tests, regression tests, especially for external libraries to make sure that they don't have any issues with like performing the job that we assigned to them. But then also like additional tools which are available for Julia, and I think that's one thing that really helped us in this domain is that you can have a statistical analyzer, a linter that works, and a really good doc system that helps us out. A final word about how we switched. You start with a team of 8 people that only ever wrote MATLAB. How do you move people to Julia? It's a completely different work environment. You definitely have to fiddle with the knobs a little more. You know, like running Julia is not a day-to-day. Like it's not as easy as just opening your MATLAB environment and running it. You may have to, like revise doesn't work because you changed the type, and so you have to reload your thing. Like all this has to be taught at some point. In the end, we started by providing quite a lot of testing, quite a lot of training to developers, really focusing on the extra features compared to MATLAB. So like how to package things, how to test things properly, how to contribute to docs, and making them contribute to docs as they're part of their training process. And finally, once we give them an initial feature that's not too critical, so they have time to like iterate on it, work on it, and get feedback, we can finally just let them loose on the code base and let them learn by doing. A little word on return on experience. What really worked for us switching to this language was we unlocked a lot of performance. Honestly, like it's not really a problem. I think we actually spend more time scheduling threads than actually running them. So it's quite, this is because we still have this reflex of using really big machines. So we have like 64 core, but we really don't need them. The package ecosystem has worked great. It's really saved us a lot of time to be able to import an orbit propagator or whatever. Our workflow has been fully modernized. Nowadays, all our tests run in CI at every commit. Everything is fine. It's not so easy to do this in MATLAB or any other proprietary environment. And in our company, we obviously deploy a lot of lots of things to cloud infrastructure. So far, it's been going great. So that's definitely a positive point. Things that worked less great is how do you actually organize a big project in Julia? That's not very clear. It's very hard to find. People say that you should like go and look at the Julia project itself because it's a great example of how it should be organized. Maybe, but it's not very clear like how to build things. If you have suddenly like multiple packages in your mono repo, how do you build the docs? A bit difficult. You can get through them. You can figure it out. Everything works. It's just a little bit of a pain point pushing through this hurdle. And obviously the debugging experience, I would say like it's the biggest shocker for anybody who comes out of MATLAB. It's not that it doesn't work, but it's like pretty difficult to get anything out of the debugger in Julia right now. There we go. In summary, we have built this tool. It makes cool videos. It also helps us to design constellations. We're able to size future constellations. We're able to run our current constellation. We're able to change all the algorithms that we want. It's pretty easy to deploy. And in general, the team is quite happy to have switched to this language. Like now new projects are happening organically in this language. If you have any questions, I'm happy to take them. We have 6 minutes to take them.
Talk. Anybody question?
Thank you, and what a great talk. I want to ask you, how do you deal with logging? How do you do it, and what is its performance cost, both in terms of speed and allocations?
Sorry, with floating?
With logging. How do you log the data from the state?
So the logging system has been designed so that entities expose an API to say, okay, these are the things I would like to load. So the first step in the logging process is that we use all the available threads to go and find from all the entities what they want to log. We move all this in memory to a first log snapshot, which is then transferred to another thread for writing to disk. So we let this whole snapshot live, like just in normal RAM, send it to a thread to write it out, and then resume our simulation in the meantime. So as long as it takes less time to write the snapshot to disk than to run a single step of the simulation, we should be able to manage. In some cases, we are logging bottlenecked, it's true.
So it's configurable, like you can choose what you want to log and what you don't want to log.
So maybe something I can go back to. So right now we're still in the development process of the system, so that's why the logging system lives on the other side of the line. You basically have to explain, when you set up your simulation right now, you have to explain to the logging system which entities to go and have a look at. In the future, something I would really like to have is some sort of like publisher-subscriber system. Only one subscriber, the logging system. But you could set at the start of your simulation all the topics you want to log. A little bit, if you've played around with drones or PX4, like it would work exactly in this way.
Hi. Thanks for the great talk. I'm developer of the satellite box, so I'm glad it's being useful. If you have any
we are glad to have it
please.
available.
If you have any suggestion, please let me know. But what I was really interested was on that visualization. How you create that? Do you have some kind of script available for us? Because it's very nice. It would be very helpful for futures I would like to implement.
So right now we take our log file, which is some sort of GLD2 archive, and straight up throw it into Geomachy. So we had to like kind of convince Geomachy to work for this. I don't know if you've played with this, but it's not always so easy. This package is great, by the way. Like I love it, but like there's like some small issues that we always have to iron out. In terms of releasing packages, it's something that I've asked about a couple of people around at JuliaCon, just like what general process should be followed when you work in a big corporate company and like things have to be signed off on by lawyers, etc. I don't know if we could release this out, but at least releasing our fixes to Geomachy, etc. could be interesting.
Okay, thank you very much.
One last question.
One very quick one. I understand that your simulation basically runs on discrete time, right? Like the steps are the kind of discrete steps, like so at some point one state and then the next step is a different step.
Yeah, exactly. Yeah, yes,
okay.
That's true.
Yeah. Yeah, I just wanted to confirm.
Speaker wants to come up already to connect, and then we can do one more question as you get your laptop going. So one more question, please. All the way back.
In your benchmarking pipeline, do you use any open source benchmarking tool or?
We use benchmarktools.jl for benchmarking.
Okay, nice, thanks.
Thank you.
So do answer if you still want to.
Say.
Thanks, everybody.
Otherwise, there is an HDMI.
Yeah, it's not coming. You said you have this? No. No, the HDMI. Yeah, okay.
Yeah, let's go like this.
Yeah, let's try.
Yep. Yeah. All right,
Okay.
I'm gonna give you one more minute to get all set up. I think that's where we are ready. So we have another Roman.
French Roman. Another French Roman, no?
Yes.
I think he's French.
I'm guessing so, yes. And also you're sticking to the theme of orbits if you were at the previous talks, but I think in a little bit of a different way. So we have Roman with what's new in bifurcationkit.jl. Take it away.
Thank you very much. So it's a very great pleasure to be here today. It's my first JuliaCon,
but I've been working on using Julia since 0.3 or 4. So I'm glad to see to put faces on all these names I've seen on Slack or whatever. So today, of course, it's what's new with Bifurcation Kit. I've been presenting this 2 or 3 years ago, so hope there have been a lot happening since then. But I will focus on computing curves of bifurcation of periodic orbits and their codimension to bifurcations. Okay, so don't worry about it. This is the very latest addition to the software, and you will see that's a very practical problem. So the outline of the talk is I will present very briefly what is bifurcation theory, so that people who doesn't know it don't get lost. And people who does know it will be bored. Computing periodic orbits. So you see what are the different methods that are used in the package to compute periodic orbits. So this is the math part. You know, it's in blue. And then we will switch to the new API of Bifurcation Kit and the consequences of it. And then I'll break my number 1 rule, which is not to make real-time simulations, but for you, I will break it. And we'll put into action this goal of computing curve of bifurcation. I'll show you how it can be very useful. And then we will conclude. So let's move to the first part, which is, let's say a few words about bifurcation theory. In a nutshell, it's to study equilibria and periodic orbits of ODE. In Bifurcation Kit, n can be millions. And if you look for, equilibria, which are points solution of the ODE that do not evolve in time, so these guys here, they are these equilibria are basically the zeros of F. Okay, so as an you also can compute zeros of vector field as a byproduct of these tools. Okay, of the tools I will present. So now the question is, those equilibria are stable or not dynamically? And so the mathematical result is basically that the point here is a bifurcation. So for a specific value, PBIF is a bifurcation point if there is an eigenvalue of the Jacobian with a 0 real part. So why is that? Because usually when you have this, you have a change of stability of the equilibria. So for example, you will give birth to oscillations. Or you have a new local branch of equilibria nearby. So here on the video, I did this for you. You have a parameter here, x here, and in bold, this wide line is the stable part, or all the real part of the eigenvalues are negative. Here it's unstable, so we have at least one eigenvalue with real part positive, and so here, when you cross, you have a 0 real part, so that's a bifurcation point. Okay, so it's a fault in this case. So it's a practical example of what this slide means. So of course we can do the same. We can do the same for periodic orbits as function of a parameter. And of course, if we can solve the right eigenvalue problem, we have the same kind of results, meaning that if we have a 0 real part eigenvalue, it means that we have, I'm simplifying things, but it means that we have a bifurcation, so a change of stability or new branch of local orbits. Again, we have an example here on the right. So here you have the object. This is a periodic orbit. Okay, so paired 6 in this case, and we can follow it along the branch, and you will see you see here. These are the Floquet coefficients. We have something with 0 real part here, so it means we have a bifurcation. So up just after, we have these green dots, the pair doubling in this case. And so you see that's quite similar to equilibria in this case. Okay, so now a very simple example with a Stuart-Landau oscillator. We consider this two-dimensional ODE. Z dot equals Z times this scalar thing. And so when P is negative, we have obviously the equilibria Z equals 0, which is solution. It's attracting the solution. You see all the flow is going to it. It's because when Z is close to 0, the dynamics is basically linear. It's Z dot equal Z times P plus omega. As P is negative, it converges exponentially fast to 0. If you put P positive, then now the equilibria is repulsive. And you see that the dynamics around, is expelled, and it converges to this circle of solution, which is a periodic solution. Okay? So that's basically the Hopf bifurcation, where you go from damped oscillations to true periodic motion. So this was the math, but numerically, how do we do this? But we continue the zeros of a function as a function of a parameter, p. We compute the equilibria, so we compute the spectrum of the Jacobian. We detect when we have a bifurcation, meaning that we detect the unstable eigenvalues, the number of them. If we have a zero eigenvalue, it means that nearby there must be new branches. So for example, here in this case, I'm following the pink one. Here I have a bifurcation, so I have a branch around. In the case where the eigenvalue is imaginary, purely imaginary, it's the Hopf bifurcation. We just saw it, previous slide. And once we've detected this, we can branch to the new solution and go back to one, detect all this, and then you can end up with this zoo of branches, which is for the 1D Swift-Hohenberg PD problem. Okay. So that's for the math. Now let's the first part of bifurcation theory. Now we will review the three different ways in which periodic orbits are computed in the package. The first one, and the first one I programmed, it's called the trapezoid method. Very simple. So what we do is we look for periodic solution. So periodic solution of the Cauchy of the ODE. So up to a change of time, we can still assume that the period is 1, but then the period of the solution is multiplied by the vector field. So this is the form that we use. Okay, so there are two unknowns actually. We need to know the orbit, the shape of the circle somehow, and we need to know the period. Okay, so these are the two unknowns that we are looking for. And what we do is basically we discretize the circle, so x0, xt over m, x2t over m up to x1, and the period. So that's our unknowns. So there are many, if m, the number of slices, is large. And then we discretize e. So very briefly, you recognize here the time derivative. Okay, this is the part. And then we have this minus the h is t over m. So we have t over m. And because we have a trapezoid method, we have half of the mean of these two neighbors' slices. Here we have the periodic boundary condition. So that's this one. And then we have a phase condition because every translated version of a periodic orbit is another one. So if we have a non-singular problem, we need to have this. And so on the right, this is the example I was showing you a few slides ago. So this code is very optimized, the radius allocation. With radius allocation, we have 7 different solvers for PDEs. So you can choose how to solve the linear problem. It runs on GPU. We can automatically branch from Hopf bifurcation and the bifurcation of periodic orbits. Here you have a automatic branching from the Hopf point, which is in red. Another way is to look at the flow. So sorry, I forgot to mention the previous method works for intermediate number of unknowns, say 10,000. Okay, you have 10,000 unknowns, you can still use it. For this one, we have basically no limit in the number of unknowns. And it's a different way to compute periodic orbits. Is basically we look at the flow, and once the flow hits the same point again, okay, if we have a fixed point, so x0 and a certain t, then we have a periodic orbit. Okay, so we just look for x0 and t. And so you have an example on the right, which is for a PD called the Brusselator. You can see here we have 500 unknowns, and it computes this relatively easily. So they are different, again, because we want to handle ODE, PDE, non-local problem. We have different solvers that are implemented. You can define your own flow, okay? Or you can use wrappers to differential equation.jl. That's already provided in the library. It runs on GPU. You can branch automatically from Hopf bifurcation, pair doubling, bifurcation of limit cycle automatically. From probably 2 months ago, I added the normal form for pair doubling and Nemax-Acker bifurcations. It's a bit technical, but this is basic. There are 2 softwares that can do that now, MatCont and this one. So it's very robust tool. This tool is very robust. Standard shooting, I mean. Finally, the last one, it's relatively recent addition. It's collocation method with parameters n, tst, so which is the number of time step, and a collocation number m. So very quickly, we look for periodic solution xt as before, solution of this ODE in rescale time. And so we start by basically meshing the time. So these are the mesh points. They are tau1, tau nt plus 1. So they are roughly, they are NST mesh points. And they can be adapted. They can be changed, okay, depending on the solution. And on each small interval, so tau j plus 1, we do an affine transform so that we can assume that we can rescale this time interval to -1 and 1. And then we rescale the problem, the ODE, in this interval. So now I have this, I've changed a bit the period on this, this multiplicative factor. And on each one, each xj is going to be approximated by a polynomial of size m, of degree m. Okay, a Lagrange polynomial. So that's the that's the basics. That's the basics of the method, and you can see it here in use. For example, I will stop. You can see that here we have a nice, relatively cosine-like periodic orbits, and as the parameter is increased, it converges to a periodic orbit with a long period, here already 40, and then we go to 150, and you can see that the mesh is being adapted to capture this homoclinic orbit, which is, for those who doesn't know, somehow a periodic orbit of infinite period. So this is state-of-the-art method for ODE. So it's used by Otto, Matcont, Coco. It's very precise. You can do mesh adaptation as I show. And it's been improved a lot in the past 6 months in bifurcation kit. So it's non-allocating. The Jacobian is really is analytical. We have a dedicated linear solver, which is about 5 times faster than what it compared to the backslash operator. Sparse Jacobian-free methods to use for PD. And again, you can do branching from Hopf, pair doubling, and bifurcation of the limit cycle or automatically. And this is basically the only software with Matcont which can do compute these pair doubling and Nemax-Acker normal forms. Okay, so that's it for the math, and now I'll go into more detail into the library. And so, what is bifurcation kit? Finally, if you didn't know, it's after 10 minutes. It's basically a library for numerical bifurcation analysis of, at first, large dimensional equations. Okay. Here is a quick example of how you can, let's say, look for a compute a bifurcation diagram. For example, here you give a vector field, which is here a cubic. You give parameters. So here we have 2 parameters, but we only use a p in the vector field. We define a bifurcation problem where we give the vector field, initial condition, parameters, which parameter we want to continue with. So in this case, p. And then we call continuation with a continuation procedure, which is pseudo arc length in this case. So this PALC is a bit like the ODE times taper in the SciML framework. Okay, so that's the new API. Okay, the old one, we were basically giving everything to continuation, and it was a mess in the code. Very difficult to dispatch on the objects or to build a very big library. So that was a massive change into the library, but it allowed a very big expansion in the capabilities. And now we have an organization. I'll show you if you don't know about this. There's an organization where we have different plugins. So for example, we have a plugin for daily differential equations. So if you don't know what they are, I'll show you up. So these are equations like this, which depend on a delay. So usually they give a lot of rhythms and periodic orbits. We have also a very recent addition is computing homoclinic orbits. We can also coupled with GridApp, so it's very nice. So to compute a solution of PDEs with using finite element method from GridApp, and you can define a GridApp bifurcation problem and do the continuation and the bifurcation diagram using basically the same method names as in bifurcation kit. And the last addition is a generalization of continuation in 2 parameters. So now we can continue surfaces in 2 parameters where the z-axis can be very large dimensional. Okay. So the API consequences are basically problem can be automatically created. The solver, linear solver, eigensolvers, they can be tailored using dispatch. We can use very more sophisticated libraries, so compute periodic orbit with 4 methods. I presented 3, but there are 4 methods, and the solvers are dispatched on the type of these on the type of the method used for defining periodic orbits, and so on and so forth. One last thing that is very useful is the result encapsulate everything that is needed to rerun the computation. So, for example, in this case, it's a branch of periodic orbit, and the algorithm, you can see that it's a pseudo-arc length continuation, and you know something about flow K coefficient has been inserted into the... So it's been automatically created, and it's saved into the branch. Same for the problem. It's a bit like the SciML solution type of... so everything is recorded in the branch. You don't lose anything, okay? You can rerun it just from that. So now we have... if we compare to other software in the field, we are very close to MatCont in terms of functionalities. We share a lot of functionalities with MatCont. But there are a few things that we are very different. So for example, we can monitor function along the curves. So that's very, basically MatCont and bifurcation kit can do it, and Auto also. For periodic orbits, we have many methods, and the use of the fact that we have many methods to compute periodic orbits is because we can tackle very large problem or very small problem with more precision. So you have the choice for that. Otherwise, you're stuck with a small problem with the other frameworks. I won't enter into the details, and the blue box is about periodic orbits, and what is missing compared to, let's say, MatCont is we don't have a very high-dimensional bifurcation of periodic orbits, which are embedded into the bifurcation kit. But to me, one very important thing is we have testing in bifurcation kit, a lot of testing. So the CI is more than 1 hour to test that the results are right, right? You can trust the result. In Auto, we have a bit of testing, but it's more about that there's no bug, that the functions run. And we have not discussed branching or, let's say, large dimensional case. Okay, that would be another way to compare the different frameworks, strength and weakness. So let's, after this very general overview of the recent edition, I would like to give you a practical example of how to use it in real time. We look at this, this complex equation. We don't really care what is. It's just that it is complex enough to provide interesting dynamics, okay? And so here we have a bifurcation diagram that is produced, and I hope I can do that like this. Yeah. Plus, everybody can read, I hope. Is it large enough or? Okay. Thank you. So here the vector field is programmed, is already derived. I take an initial condition, which is the 0, the equilibria I want to compute, okay, to follow. So as I told you, we define a bifurcation problem like this. So I put the vector field, the initial condition, the parameters, which are all this named tuple. I want to continue with the parameter k8. Why not? I want to continue between minus 0.1 to 20. And then we continue it. It's computing the branch. The plot is on the right. We have a half bifurcation here, another one here, and the blue one. And they are given in the... So if I type BR here, the result, I see that I have basically information about the bifurcation point that have been shown. So what does it mean practically? For example, if I go here, just after the red dot, the equilibrium is stable. So we can simulate it here. So after the bifurcation point is the bifurcation point plus something. So I do that, and you see nothing changes much. It converges to a different equilibrium, but which is nearby. So if I go before the bifurcation point, in this case, I see oscillations. Okay, so that's what I told you before with the Stuart-Landau oscillator and so on and so forth. If I compute the normal form of, I think it's BR2. Yeah. So here on the right, it tells you that we have a half bifurcation and the period is about 11. Okay, so if I zoom in on, I should be able to see 11 here. But we can do something more interesting. We can compute the periodic orbit. So what we do here is, I want to branch from the second point, which is a hop, and I'm going to use collocation with 50 time step and collocation order 3. Okay, so let's run this. It's compiling. I hope it's not going to crash. It would be a disaster. Okay, we got it. So we have a branch coming out, you see, and we have seen different bifurcation points along these things. So here we have an orange one, which is interesting, which is an Emacs sucker. So for those who doesn't know, we'll play the game again and simulate the dynamics after. So before, sorry. So it should be, yeah, that's it. And we see nice oscillations before the Emacs sucker bifurcation. And if we go after, what we will see are, you see breathers like this. So like we have two oscillations, two frequencies into the dynamics. So we have the first dynamics. So let's have a look at the normal form. And so if we compute it, it tells us that basically the underlying frequency is 15 and the other one is about 100. Okay, so this is nicely predicted. So now the thing we want to do is, so that explains this diagram here for you, hopefully. But if I change the parameter K7, for example, it will, and we run all these simulations, so all these branches, you see the bifurcation point will vary a bit, okay? But this is very troublesome. And if I put it on top, so if I look at the same plot but from the top, here I see those bifurcations. So I know here I have oscillations. In this area here I have torus solutions, and here I have no oscillations. So there should be a way to jump from this point to this point automatically without computing everything else. Okay? So of course there is a way, and it's called the curve of bifurcations of periodic orbits, the big word but simple concept. And here you can see that we can compute the curve of Emacs sucker. They are like this, and we can detect higher codimension, so Chance-Ciné bifurcation in this case, and here you have the fold. Okay, so that's basically the last big addition to the software. And it's the numerical method I explained in the doc. I will be a bit quicker now. One last thing. Yeah, to compute this normal form, there's no analytical formula. So it's been tested against approx.fun. And to my knowledge, this is the only software where these normal form have been tested. Recent improvement is we can do the same with two parameters. So we can compute periodic orbits. These are periodic orbits here. And you can, with two parameters, so you can see the same on the right. So it's very useful to find isola, for example. We have also improved a lot the linear solver of collocation. So the solve goes to 3 milliseconds, in this particular example, to 300 microseconds. So it's almost a factor 10. So this is a method that is used in auto. And that's it. And I want to conclude now to give time for questions. So in conclusion, the state of numerical bifurcation analysis is well advanced in bifurcation kits, at least for ODE. And to my knowledge, there is not much to do. To go for higher codimension would be meaningless. Nobody does it, and there's very little use for that. Okay, so this is basically feature-full, roughly speaking, in this direction. There are many solvers available. For example, the last solver I was mentioning, which is faster, should be useful to SciML as well. They are Jacobian free. I'm not sure that all of what I presented today works on GPU. Should be in principle. We could do the same for delay differential equations, but that's in red, so it's a massive work. If you want to help, an interesting thing would be to make a GUI out of this method. That would be very useful, I think. Or you can, so it's in orange because it's a bit of work. Simple and useful help with the issues or provide feedback on the API. You don't like the way it's framed. This is very useful to us. Something very difficult is integration with nonlinear solve and linear solve. Right now we rely on a custom linear solver that are from Krylov-Kit and so on and so forth, but Newton is very simple. And that will solve probably the problem of in-place and out-of-place method in the library. Complete a full integration with readapp that I mentioned. So basically half of the library is linked with readapp, and I think that would be very nice. Distributed computed. That would be a nice way also to improve the library. I don't know if it's simple. Simplify the integration with dynamical system by George Datseris. I think that would be very nice too. The integration with modeling toolkit has been done, more or less, I would say, thanks to Torkel and Lohmann, and this is very nice. You can just, it's very nice framework. I would like to do the same with method of lines and etc. And with this, I will thank you for your attention and take any question if you have any.
Thank you, Romain. Any questions? Hands up.
Hi, really nice talk.
Thank you.
I understand you have 3 or 4 methods for continuation of periodic orbits if you branch from a codimension 1 bifurcation, but from a codimension 2, which methods are available?
The same. But
the same, exactly the same.
But for the dimension 2, so it's you cannot change. So if you've computed using collocation here, you cannot change to compute this one.
Okay.
I mean, that would be doable, but yeah. But that's a lot of work.
Okay.
Yeah, thank you for the...
Thanks a lot for the talk. I have a question about the very, very last part, the ... What about difference equations?
Oh, you mean discrete time dynamics?
Yeah.
I have 2 hands only. There's a beginning of it in the code. It's a bit hidden because to compute normal form and bifurcation of in the shooting case, it's basically a Poincaré return map. So it's discrete time dynamics. So Neymark-Sacker bifurcation, what else? Period doubling, they are already encoded. And the detection of these bifurcations, which is a bit different from the continuous time dynamics, is already coded. So I think what is, at least for code dimension 1, what is missing is an API, which takes this thing. Of course, for codim 2, you need to program it. Yeah, I mean, for example, I don't know, Chancinet is already programmed. So yeah, some of the tools are already present, but they are not outsourced for the user, I would say.
Okay. Is that something that can be expected sometime?
If you open an issue and if you want to help, I can guide. Yeah. Is it okay for you? Yeah.
One short final question.
Short one.
But it's not easy, huh?
At what extent do you use automatic differentiation, for instance, in your continuation methods and so on to create Jacobians? And what are maybe possible open questions in these directions?
I'm not sure I understood. You want to know if I use AD for the Jacobians?
Yeah.
So right, the default now is forward diff, and it's dense Jacobians. But you can pass your Jacobian in the bifurcation problem. You can pass your own. I think it would be nice to use abstract differentiation so that the user can choose the framework. And for periodic orbits, there's a mix because I want it to be fast, non-allocating, sparse, and so on and so forth. So they are coded. So there's a mix of AD and analytical formula, or sometimes it's a full analytical formula. Yeah, it's very optimized for that. Does it answer your question?
Yep, okay.
Right. Thank you.
Thank you.
Applause.
Thanks.
HDMI or do you need USB-C?
USB-C.
All right, let's get this going. Feel free to take the conversation backstage. Watch out for the cables. Right. I think you maybe need to switch what the master screen is.
Okay. Just do this again. Let me try HDMI.
I think you're.
Need some time. Yeah.
Okay.
All
cool.
right. And presentation. Let's see.
Not sure why it comes like this.
Is it a button exchange? Maybe that one.
Yeah, that's the one.
Yeah, it's sort of in screen mirroring mode or something,
Yeah.
I guess.
Okay. Have a PDF. I'll try that.
Yeah, this might work as well.
Okay, that's better.
Yep.
All right. All right, so now we have Nishant for Kubernetes client for Julia. So thank you and take it away.
Thank you. Hi everyone, welcome to this talk on kuber.jl. Kuber.jl is a package that is OpenAPI based and it's a Kubernetes client. My name is Nishant. I work on Julia Hub. So yeah, as an introduction, so I write cloud-based software at Julia Hub. So working extensively with AWS, and we write software for deploying distributed workloads on Kubernetes and AWS. And so far, our code has been written in Julia. So in this talk, I'll just go over the kuber.jl package and its basic design and usage. And we will see how we can deploy a Julia-based web server and how we can scale it from Julia. And we'll also talk about a little bit of some advanced operations. Okay. So I just want to give a brief overview on Kubernetes so that we have some context for the rest of the talk. So Kubernetes is a open source system which was originally developed by Google. Now it's maintained by the open source community. And what it does is it orchestrates containers on multiple machines on the cloud. And as such, it makes the job of deploying containers, starting up instances, all of that easy because it's all automatic. And it's mostly written in Golang. It's also popularly referred to as K8s, so you might see that a lot. And it's happens to be one of the most widely used software systems in the world. Okay, this is an architecture diagram of Kubernetes that's taken from the Kubernetes documentation. So the heart of Kubernetes is the API server here, which is the central point for most of the communication. Much of what we run as Julia containers, they run on the nodes, and The nodes have two components. They have a thing called kubelet, which is a daemon process, which is responsible for actually orchestrating the containers within that node, and it talks to the API server to get details on what it needs to run. There's also something called a kube proxy, which manages networking. So if you deploy something on this node and you want to access it from outside, it's the proxy which does the work for that. And there are a few other components. So what you see on the top is there's a controller manager, the CM, which looks into these jobs, and as their state changes, it does work to get them ready. Like if you launch a container to do things like bring up the container on that node and basically bring that system to the desired state. Then there's the cloud controller manager, which talks to the actual cloud. So if you're running this locally, then it doesn't do anything. But if you're running this on AWS, then that is responsible for bringing up your machines. Okay, moving on from this. So I just put up an example YAML file. Much of what you submit to Kubernetes is written in YAML as a standard. And whatever client you use takes that YAML, makes it an API request, sends it to Kubernetes, and then Kubernetes deals with it. So this is just a simple Julia application. So you mentioned the Docker image of Julia here. You have a command which just adds a package and runs a method in that package. And optionally, you can have some data, some external data. So for example, here there's a Git repo. But you can use things like NFS or S3. And there are a few other options. We'll see them later. But this is a basic structure for context. Okay. So why did we write a Julia package if we can just submit YAMLs and be done with it? So YAMLs are static; they're just text files, and you can submit them if that's what you wish. But with Julia, you can do a bit more. So you could write your own client for starters, as in a command line client or a web client. So typically, people use thing called kubectl as a command line client, and there's things like the Kubernetes dashboard. If you're just getting started and you just want to experiment with this, you could maybe write your own client like this. Slightly more advanced, you could write a distributed CI service, which is quite useful. And in fact, we had one of those running the pre-Julia 1.0 days. So basically, you could write using github.jl, you could write a GitHub webhook listener, and then based on what packages are getting registered, you could start jobs on your Kubernetes cluster. So the practical use of that was that we wanted to test reverse dependencies of a package. So if a package has a lot of dependencies and somebody registers a new version, we want to make sure it doesn't break like a bunch of packages. So that was one place where we used this. Apart from that, you could write a web application for your company or your organization to submit jobs, because not everyone's familiar with Kubernetes. They wouldn't submit YAMLs, right? And maybe slightly more advanced, you could write your own autoscaler or some kind of automatic manager, as an example. So Kubernetes.jl gives you the tools in order to write that. So we'll talk a bit more about the API which makes that possible. Just a small note on my dev setup. So I'm just running OpenSUSE Linux on this laptop, and I have K3s on it. There's the link for K3s in case you're interested. K3s is a
lightweight Kubernetes, which is great for learning and testing on a single instance on like your laptop. Yeah, and my K3s is configured to use Docker, so you can build Docker images locally on your laptop and make use of it in your cluster. Okay. Brief intro on kubectl. So this is based on OpenAPI. So much of the code here is generated from a specification file, and we have some wrappers around it to make it easier to use. There's a link for that. It's open source, so you can install it with the --add command. And the API is fairly low level in the sense, not close to the metal, but low level in the sense we expose the API as is, and you might find that you might want to write wrappers to do some common tasks which you might have. But it's pretty powerful in the sense that the API is pretty close to the spec that's provided. The package functions are modeled on this idea of verbs and nouns. So nouns are just the entities that you have on Kubernetes. So typically you might use something like a job to run some Julia code to completion. Ultimately, everything becomes a pod. It's like the basic unit of Kubernetes, and the pod contains the container that runs your code. And there are higher level ways of, I guess, mentioning what you want to run. Like there's a deployment, which is what you would use for things like web services. You can scale deployments in a certain way. And apart from jobs, there are things like networking. So there's a object called service, which can use for load balancing. And then there's namespaces for isolating the various resources. So all of these nouns can be passed to methods, which are defined in terms of verbs. So you could get details about it, you can update, you can delete, and you can watch those changes to those entities. And we have some helper methods. So for example, we have setNS, which can be used to change the namespace of your current context. And we have setretries, which we use in production because you want to make it more robust in production. So this is just like the basic code, basic hello world example, I guess. So you just say using Kuber, you build the context with Kuber context, and you set the server here, and you pass the server endpoint. And over here, I'm just running a get method on pods, and I mentioned namespace as nothing, so it selects all namespaces. So I haven't shown the output there. It's fairly large. The output renders as JSON, but it's not JSON. It's actual Julia structs, which we've generated from the OpenAPI spec. And that's useful because you can then index it and get the specific field that you want and filter it. And we'll see an example of that later. So just want to talk about a brief example of deploying Julia web server. So I'm going to start with what's called a config map. So any application that you deploy has some config. So I have a sample application here. So I'm using Postgres database. So I have some Postgres credentials here, like the password, the user, the host. And a config map is an entity in Kubernetes. So using kuber.jl, I can submit a config map using the put_bang command. I have to pass the symbol config map as a second argument there. And in this case, I'm using YAML, so I'm using the YAML package, but what it requires is a dictionary ultimately. So you could just use a dictionary. The second piece of a web server is the actual deployment itself. So this is a deployment. And I've just highlighted some important parts of this. So you can mention the number of replicas. So that's the number of containers you want. It's just set to 1 for now. There's a port 8080. And then there is the Postgres secret we just created. We just mount it as environment variables here. So once again, it's the same API. It's just put with exclamation, but you have to mention that it's a deployment there. And moving on. And the final piece is the load balancer to expose this API outside of Kubernetes. So here we just say, take the port 8080 of your container and map it to port 80, which is a standard HTTP port. And once again, the same API, but you mention service. And when you do that much, you get your web application running. This is just a sample web application that I've written. And here's just the local IP that it generates. If you're running this on AWS, you will get something different here. Like you might get the load balancer name, actual name, and you might use it in your DNS service and get a nicer name from that. Yeah. Okay, so that was about deploying a web server. Now, what if you wanted to scale it out? You had one container, you want multiple containers. You can use the update method. And to update method, you just say you want to update a deployment, the name of the deployment. And then you need to specify that you want 2 replicas. So when I said the API is low level, I meant this. So ultimately in your code, maybe you want just a one-liner. So you can wrap around this. But right now, basically, it's like this. So once I scale it to 2 containers and I list the pods, I get 2 of my demo apps instead of 1. So now the app is scaled to 2. Similarly, you can scale it back down. You can change that to 1. You can even change that to 0. It's going to just sleep in that case. There's not going to be any apps. And then you can change it back to 1 when you need it. And finally, we have the delete API, with which you can delete the resources. So delete API can be used for, in this case, it's just used for deployment, but you can delete the other resources as well, the load balancer and the config map. Okay, so that was about web server. Let me just briefly talk about using Julia's distributed standard library for doing distributed tasks. So what I'm going to show is having a master container connect to some worker containers. And to communicate, we are going to use clustermanagers.jl, which is an open source package. So this is actual code. Some of the code is hidden in this common file, but most of it is here. So on the left side, you have the master's code. Right is the worker's code. So you just say using cluster managers, and we have this cluster manager, elastic manager method or constructor, which starts up a server on the master for the workers to connect to, and it happens asynchronously, so it's going to come here. And we have this while loop here, which just waits for n workers to come to, so we want 3 workers here, so we wait till we have 3 workers, and we sleep for 5 seconds while we do that. So on the worker side, we just have the elastic worker method being called, and as the workers connect, n workers is going to get incremented, and at some point it's going to be equal to 3, and That's when we come out of the loop. And inside this estimate pi method, I have a pmap. And you can use all your distributed macros there as well, like at everywhere, spawn at. And that's going to make the workers, that's going to send out the command to the workers to start working and return the result. So yeah, that's how you would use distributed package. Oh, sorry. Okay, thanks. Okay, I'll just go through. So this is a corresponding YAML file for the master. I'll just quickly go through this. This is just a master node with the same port being exposed, and we need to have a service as well for that port for the workers to connect to. And this is the worker specification. So for worker, we just mentioned the number of workers as parallelism here, and we want to limit it to 1 CPU. So we mentioned the request here. Okay, so the output looks like this. It's going to wait for some workers for some time. Then finally, it's going to get the value of pi there. And if you list the containers, you're going to see 1 master and 3 workers. I just put this slide here just to mention that you don't have to use distributed. You could use something like ZMQ. There's more details on the ZMQ website. Okay, just a brief note on GPU. What do you have to do to run GPU jobs on Kubernetes? Well, first of all, you should have GPU hardware. On your container images, you need to have CUDA installed, CUDA.jl. You need to have NVIDIA drivers, if it's an NVIDIA GPU, installed on your node. And you need to specify nvidia.com/GPU1 or any number that you want in your specification of the job or the deployment. You also need this NVIDIA plugin that's freely available on GitHub, installed on your cluster. And finally, some environment variables that needs to be set. So I had to just go through this to make GPU work, so I thought I'll just mention this in case it's useful for anybody else. So coming to the watch API, so we have an asynchronous API which lets you watch resources and get updates and then take action on those updates. So why is asynchronous good? Because if you want to watch some resource and you keep calling the API server, that's just expensive. Watch is just one method that you call, and then you keep getting a stream to your closure, and then you can do whatever work you want here. So where is this useful? So it's useful if you want to write your own monitor. Let's say you have some instances in your office and people in your office are using this cluster and you want to keep an eye on what's happening. So you could write a watch on, say, the node resource instead of pod. And you could get a list of changes happening to the nodes in your cluster. And similarly, within the closure, you can use the write APIs, such as put or update, to make changes to the nodes if you wish. Okay, do I have time? Okay. Oh, okay. So as I said, Kuba.jl is based on OpenAPI.jl. So 2 days ago, we had a talk from Tanmay about generating a client using OpenAPI. So Kuba.jl is such a package which uses OpenAPI. So if you ever need to use custom resources, you can generate the API, and it's fairly easy to use it with Kuber without having to modify Kuber. You can keep your API module in a separate package, And in the Kuber context method, you can just specify that package as API model, and that gets plugged in and it gets used. It's easy to use that way. All right, so just go through the summary of what we talked about. So we just presented kuber.jl, which is based on OpenAPI. Went through the basics of deploying a web application. We discussed distributed Julia as well as GPU workloads. And we talked about the Watch API, which lets you get change notifications. And we talked a little bit about the internal details. Yeah, so in conclusion, having a Julia programming interface to Kubernetes is great because you now have one language for your data analytics, your web programming, as well as Kubernetes programming. So if somebody wants to get into Kubernetes programming and they are familiar with Julia as a machine learning or data analytics language, they can now start using Julia for Kubernetes. Thank you all. Thank you for this.
Any questions? Yeah, one more already.
Hi, thanks for the talk. I had two questions. One was, do you use the .cube config file at all to pick up configuration settings?
No. We have our, I mean, we don't look at configuration in this case. So if I have to show an example. So here's an example of something that connects, that actually works. So we just use a token, which is a Kubernetes secret, which is linked to a service account, which has access to the cluster. And that's it. That just gives us access to the cluster. Yeah.
Okay. My other question was about errors from the API. What do they look like? Are they just raw JSON, or are there special like Julia types?
It depends on the error. So it would be, I think we use downloads.jl, I think. So you would, if you get a 503 error, then it would be like a downloads.jl error. Yeah.
Okay. There's no custom Kubernetes errors?
No.
Okay, gotcha.
Any other question? No. Thanks for the talk.
Thank you.
Thank you. Yeah. So we have a small 10 minutes break, and then the next talk is going to start. afgelopen dinsdag workshops gehouden voordat het hier van start ging allemaal.
Een groot deel van de installaties, de AV-installaties, heb ik daar ook gedaan.
Oh, mooi. In het Nederlands specifiek? Ja, ja. Ja.
Dus die ken ik wel, dat is een gebouw.
Ja,
Dat is mooi gebouwd worden.
Ja, zeker, zeker. Dat is ook gewoon de beamer, de camera, de audiosysteem, alles werkt goed. Ja.
Die grote teamsrooms, die werken nu ook goed? Dat was een probleem, maar in het begin waren er wel probleempjes mee.
Dat ook niet zeker. Ja,
het zijn die ruimtes, als je zeg maar helemaal
ja, die achter daar zo. Dat durf ik niet zeker te zeggen, want die gebruiken als employee niet zo. Die zijn meer, dat de studenten die zo gebruiken dat. Ja, ja.
Dat waren wel leuke ruimtes om te maken.
Ja.
De virtual classroom.
Ja, ja, dus we zijn hier de camerasystemen en alles. Ja. Nee, ja, die werken nu een jaar ongeveer. Die hebben ook wel wat gewerkt hebben, wel als wat ruimtes hadden. Dat werkt wel mooi als je inderdaad gewoon in kan bellen en klinken. En dan, ik heb het niet in dat gebouw specifiek gebruikt. Dus, ja, ja. Jullie waren ook gedeeltelijk bij het ontwerp of zo betrokken?
Nou ja, weet het, ik werk als ZZP'er, dus ik werk niet voor
ja, ja.
En dat was voor een ander bedrijf. En die zijn inderdaad wel bij het ontwerp betrokken geweest.
Ja, de uitvoerinstallatie. Ja, nee, zeker een mooi gebouw geworden.
Ja,
mensen hier zo die er waren, er waren ook een paar die zeiden, waarom gebeurt hier niet wel de conferentie? We zaten wel die 2 collegezalen onderin, voor 75, we zaten net over capaciteit, dus er zaten precies 80, 90 mensen in het gebouw weer hier en al blijven. Ja, ja.
Ja, mooi.
Leuk. Kom je er af en toe nog? Of, ja, als het is.
De laatste keer ben ik in het auditorium geweest. We hebben toen de hele renovatie gedaan van de collegezalen.
Ja.
Dat is afgelopen december geweest, dus vorig jaar december. Daarna ben ik eigenlijk een poosje niet meer geweest.
Ja, ja. Volgens mij komt er nog wel weer gaminggebouw en zo.
Ja, er staat er altijd wel voldoende te doen.
Ja, ja. Ja, dat zal ik wel eventjes. Ik ben benieuwd wat er allemaal nog bijgebouwd gaat worden. Zag ik het laatste wel van dat al het schaalplannen met hoe het met de overheid en alles maar ook dat er wat iets gematigd wordt dan. Maar we zien wel. Ja. Dus kijken of die snel weer van start gaan. Ja. Jan, you want to get mic'd up?
So, I will switch it on when you're going to speak. Yeah.
All right, we're quickly gonna get started because the next 2 presentations are only 10 minutes. So I hope you're ready, Jun.
Yeah.
Then please welcome Jun Tian about the pretty much hot topic of the year, I guess, is LLM code generation and specifically how that reflects for Julia.
Okay. Hi everyone. Today I will give a short introduction to evaluate LLM synthesized Julia code. I'm Jun Tian from 01.ai. So let's first give a brief review of existing code benchmarks. The first, or maybe the most popular one is human eval. It contains 164 Python tasks. And another one is MBBP. The name states mostly basic Python problems. And we also have multiple E. It is a translation of above 2 problems into 18 programming language, and also including Julia. And for some other tasks like single line filling, which is suitable for Copilot related tasks, meaning for code completion, and also repo bench and SWE, software engineer benchmark, for real world GitHub related cases, and also live code benchmark. And today I will mainly focus on human eval. And the left figure is the original prompt input to the language model in the Python world. So as you can see in the Python, the first we have a function definition, and then followed by a doc string. And in human eval.gl, we all know that the doc string comes first, and then the function signature. So I rearranged the order of definition. So first we have a signature, and then we have a task description, and then comes the example section. In the example section, I also added several Julia doc test cases. They are mainly coming from this section. So I just reordered it. And then we have a final signature. So this is the prompt input to the language model. So what makes human eval.gl special? Of course, first, it is implemented by a human. That was me. And I fixed some bugs in the Python version. The original human eval contains several bugs. We all know that a human can make mistakes. And I added much more test cases. In the original Python version, we only have very limited number of test cases. And in human eval.gl, I added the auto-generated many test cases from the eval process. So the test cases increased from less than 10 to about 10 or 100 times. Also, I rephrased several tasks to make them more idiomatic in Julia. So including the famous one-base indexing, and also the even and odd such cases. Also, as we can see from here, I added some extra type annotations, including the arguments and also the return of the function here. So I haven't do serious comparison, but in theory, it should help the language model to understand the problem better. So is human eval.gl a good benchmark? And here I plot the number of language models solved by each task. Here I use 25 language models I can access to. So the x-axis sort the number from the easiest to the hardest. So as the arrow indicates, the human eval.gl still, the task in the human eval.gl is distinguishable. Only here, for the harder problems, here, there's a little cliff. So maybe we should add more harder tasks to this benchmark. Okay, let's go to the evaluation result. So here, the y-axis is the total 25 language models I evaluated, and the x-axis is the pass rate at 1. So note that Cloud Suite of 5 Sonnet and the model Gemini are not included. So sorry, Google, sorry, Anthropic, because I cannot access them. But the strongest model until now is GPT-4, and then followed by GPT-4 Turbo, and then GPT-4o. The strongest open source model we can access to now is the DeepSeek Coder V2 Instruct. This model, I think it was released about several weeks ago. And in the original paper, it also add the evaluation result of the Julia programming language in the report. And it claims that it is better than GPT-4 Turbo, which is here, and 69.8. And the result from the original paper says its model is 72. So slightly better than GPT-4 Turbo, but based on my test, actually there's still a gap about 2 or 3% compared to GPT-4 Turbo. 3 fun facts. First, although DeepSeek code V2 was trained with extra, I remember, maybe 6 teta tokens compared to GPT-2, compared to DeepSeek V2 chat, but the performance gain is only very little. Maybe DeepSeek can consider improve their training strategy. Second, the large models with much more activated parameters is not always result to a better performance. For example, the E-large and unfortunately also Q1 1.5. The performance is not that very well, but let's wait and see. We will have a much stronger model soon maybe in the next month, and hopefully it will be much better, even better than DeepSeek Coder V2. And the third one is that as human, actually the pass rate is not that high, especially considering the pass rate at 1, because I recorded my own pass rate here, and it's only about 0.5. So language models is much better than me, if considering only pass rate at 1. Quick test, here I plot the top 20 tokens from Julian eval.gl solutions. One of them is from myself solution, and another one is from GPT-4o. Can anyone tell which one is from me and which one is from GPT-4o? Pretty cool. Yeah. So how did you tell? Oh, cool. Pretty cool. You got it. Yeah. So a closer look into AM's performance is that large language models are very like explaining code snippets, and sometimes it's very verbose, to my opinion. And one thing that surprised me is that the language models are very good at dot broadcasting related operators. And also, the stronger the model and the less hallucination, this usually means less stupid Python-like grammar errors. Okay, yeah. And also, if we look into the language models, I'm not good at such some corner cases, I think. So we may need some interactive evaluation later. Okay, the last slides, the challenges. First, we need more practical benchmarks like JuliaIM and Leaderboard. And second one, if we want to turn from online evaluation to offline evaluation, we still need to rely on the Python side infrastructure. And the third, from code snippet to evaluation to repository level evaluation, we need more work. Currently, human eval.gl relies on test items, but if we want to move to the repository level generation and evaluation, then we need much more better infrastructure. Okay, thank you. This is my slide today.
Thank you, Junjie. We have one question time.
Oh, okay. So when we are using Julia, we are mainly focused about is like a package, like a differential equation.gl, jump.gl. So my question is the like human eval.gl support like how to evaluation the usage of package?
Unfortunately, no. Yeah, because like I said before, it mainly focuses on small task and the code snippet to evaluate the performance on some very general tasks, so not like differential equation specific.
Okay, because it's only 10 minutes talk also for the next one, please take any questions in the back. All right, let's get you set up. So you use this cable?
Yep.
USB or HDMI?
Yeah, USB-C.
Perfect. And I get the microphone there.
Very efficient.
So with two names on the program, which you're going to do it yourself?
Yeah.
Perfect.
Thanks.
All right, this is another 10-minute presentation, so we're going to quickly get started with Ben Curran for LAS data, which is apparently for point clouds, and I'm curious what the abbreviation is.
Yep. Hi, everybody. My name's Ben Curran, and today I'm here to talk about working with LAS data using lasdatasets.jl. Not entirely sure what the abbreviation is, actually. Sorry to spoil it. So to sort of give some context as to the history of this package, there are some really good Julia packages that do LAS data manipulation, particularly LAS.io has been a really good one. So I come from a geospatial company, Fugro, who does a lot of point cloud processing, and we required the latest version of the spec, which I'll get into details in a second, to be available, as well as some more bespoke features for our industry requirements for point classification. So that's kind of like the justification for why this package sort of came about in the first place, and we're definitely looking to collaborate with more people going forward. So it would be great if you want to get involved, just post an issue or send me a message. So today I'll be discussing, first of all, what is LAS, because it's not a very well-known data format, and also what the core features are of this package and some of the high-level interface going into it briefly, and then I'll make some comments on the future work. So LAS data is a format of data file that basically allows you to store point cloud data. So the basic sort of layout of how that works is like of the process of making a LAS file is like this. So you start out with an aerial scan where your plane is flying overhead and it's shining a laser beam down at the ground. And every time it reflects off something, you get these pulses of energy that we call waveforms. So there's some processing going from that waveform that I won't go into that basically then produces your point cloud, which is a set of three-dimensional points that each have attributes associated with them. So you take your point data and you can also attach things like georeferencing information from the plane, as well as some custom user data, things like dataset labels, and you basically pack that all up into a LAS file. So the LAS file itself looks something like this. And now so LAS is a specification for how to order this file, and it's gone through a few iterations. So the current latest version of this is LAS spec 1.4, which is the one that we provide support for in LAS datasets with some legacy formats as well. So it's split out into these sections. The first bit, obviously, it's a public header block. So this, like other files, stores metadata about the file contents. So you have things like file source information or byte offsets to different quantities. It then follows a set of variable length records, which are packets of data that are associated to the dataset as a whole rather than each individual point. So these things are useful for like coordinate system references, dataset tags, etc. The spec also allows you to just kind of cram a bunch of extra raw bytes in between variable length records and the point records, so we support that too. And so the main bulk of your file is going to be in these point records. So a point record contains data for your points, obviously. So The LAS spec defines 11 point formats that you can support in this, and each point format is a unique combination of what I'll refer to as LAS fields, which are like properties associated to a point, so things like its position, its classification, its intensity, that sort of thing. And you can also potentially have some extra user fields inside this, so if you want to attach, for example, a cluster ID, you can do that as well. And then, as the name suggests, you also have extended variable length records, which are like variable length records, but bigger. So they're chucked at the end of the file, and they're useful for waveform data and other things. So what does this package actually provide? What value are we giving? First of all, we provide, as I mentioned, full support for the latest 1.4 LAS spec, as well as legacy support for some of the older specs. We also have a bunch of high-level functions for I/O and manipulating the properties of your point cloud file. So this is done at a very user-friendly level. There's a lot of functions that you can use, and the main focus of that is to make it as easy as possible for people to get in and start doing things with their point clouds. We also have a LASPy-like parsing of native Julia structs through your VLRs. So rather than having at the lower level to deal with the raw bytes of your VLRs, you can pass in native structs. And it also allows easy modification of header properties as well. So because of time constraints, I'm only going to kind of go into a high-level interface for like I/O, so saving and loading LAS files. So the basic flow looks like this. So the main function that you want when you're reading is load LAS, and that takes in some LAS file, and it spits out this LAS dataset, which is like the main struct this package exports. And it's got, you can see it's got all the information kind of relating to the LAS file structure. With a little bit of extra stuff. So a design point that we made while doing this package is that the LAS points themselves are actually stored in a tabular structure. This was deliberate because often when doing things like point classification at Fugro, we want to query point properties for like a big collection of points. So you can either iterate through each point and grab it, or you can grab it from the column of a table, which is much quicker. So we rely heavily on the type tables interface for this, and that kind of helps for performance reasons. We also store under the hood the LAS fields, your position and classification, etc., and the user extra fields, so like anything you add on to the points separately, and that kind of helps to optimize multi-dispatch under the hood. And then you've also got things like your header and VLRs that are also represented as their own structs in here. And then finally, you can just call save LAS on this whole object and specify an output file, and then, yeah, you basically got the whole workflow. So as a practical example, I'm not doing live demos for obvious reasons, but basically if you have an example.las file, you might want to call it, and you can also specify things like, I only want the position and the classification for each of my points. So that'll spit out this nice LAS dataset here, and it specifies the number of points, the point format, the point channels, which are like the properties for each point, as well as the number of VLRs, EVLRs, etc. And then nice and easy here too. Once you get that, you can also just save it to another file if you want. So you can save it out to a pc.las. It's all very quick and easy and high level. So you're not actually having to worry about pulling individual bits of the file out. It's all sort of done under the hood and then shipped off for you. A more practical example is if you actually want to do something with your point cloud, you can get it in a tabular format with this get point cloud function. And as you can see, it returns this table structure with each of your point properties in the columns. And you can do cool things like if you want to add another column of a user field to your points, you can add it as a vector. So you can say, I want to add this thing property to each of my points that's a random uint16. And then once you add that, it'll modify it. So when you call get point cloud again, then it'll return, now you've got this nice thing column at the end, which is pretty cool. And one more thing that people will probably be interested in, you can also grab the VLRs out of your LAS dataset, and they're also exported as these LAS variable length records, which is basically the same as how LAS.io does it. And they're also parameterized by Julia native structs. So this will allow you to pass structs in and out if you want to. There's some extra details in the documentation if you're interested. Yeah, so there's a few things that we want to work on to sort of make this package more streamlined and better. So one thing is point streaming. This is all currently done on disk, so obviously it's unideal when you get to the tens of millions of points. We also want to add full support for waveform data, which we don't currently have, and improved handling of compressed data. And yeah, I also like to acknowledge the developers of Laz.io and the compressed version LAZ.io, as well as Avid in the crowd, who's done a lot of work on this package and some of the other reliables. Yeah, so if anybody wants to help collaborate, I'll just reiterate we're fully open to people helping out. Yeah, any questions?
I may have missed this. Do you use memory mapping or do you copy the data into RAM?
We use, I think we just copy it into RAM currently. The compressed version, I think, does it slightly differently, but yeah, it's all pretty much copied directly.
Compression, you copy during decompression, but if it's uncompressed, you could memery map.
Yeah.
And then if you have repeated calls.
Oh, yeah, we use buffered I/O streams, which are kind of similar. So it'll create a buffer and it kind of does a similar thing, but it was just, I found it was more performant than using memory mapping for whatever reason.
Okay.
Okay, seems to work. So yeah, if you want to access the slides, they're either available on go.epfl.ch/JuliaCon or you scan the QR code.
Get started straight away.
Yeah, sorry.
No worries. Okay, Felix on wave and ray optics for 3D printing, and there's some more in between there. But
Okay, thanks for the introduction. So yeah, as announced, so wave and ray optics for light-based tomographic 3D printing. So I'm Felix, I'm a PhD student at EPFL. Can just want to quickly show the picture. So it's a great place to be. So actually my building is right here. So I have a view on the lake, view on the Alps. So if you're ever at EPFL, just come by. So yeah, the title mentions 3D printing. It's tomographic 3D printing. Has anyone ever heard about tomographic 3D printing? Okay, actually one person, two person. And so who has a filament printer at home, a 3D printer? Okay, a couple of people. Who has ever tried an SLA printer, so a light-based 3D printer? Okay, a couple of people. And like even maybe a DLP printer, also a light-based 3D printer. So all of those technologies, they have a big disadvantage. They do layer by layer, and it usually takes minutes to hours to 3D print something. So what I'm working on is called something light-based tomographic 3D printing, where we don't print layer by layer, but instead we print everything at once in relatively fast speed. So tomographic 3D printing, so usually we use the acronym TVAM. And here I want to show a live video or real speed video of printing a Julia logo. So I just started here, and when you look here, after some time, there's here this gray bar coming. So this is actually UV light coming from the side, and the resin is in this glass vial here, so we rotate this at a moderate speed, so it's still real time. So what the light actually does, the light propagates into the resin, and because of absorption, the light gets absorbed and triggers a chemical reaction. And this chemical reaction needs a bit of energy to really happen. So right now, a lot of radicals are generated, and after a while, there is enough radicals, and then they create the Julia logo, which appears right now. So now the print is actually over. So within 30-40 seconds, we are able to print centimeter structure with an accuracy to right now up to, let's say, 50 or 100 micrometer, which is in terms of voxels per second, one of the fastest 3D printing techniques out there. So just a couple of physical key points, let's say. So TVAM is a single photon absorption technique, like SLA, for example, too. And the resin, it's usually like acrylate resins, and we mix their photoinitiator in there, and the photoinitiator reacts with the UV light to create the radicals. And then the setup, the basic setup is like this. So what we have on the left-hand side is here a light modulator. So what we have is we have a powerful laser. It's like a 2-watt laser. So just to mention, a milliwatt can be already dangerous for your eyes. So this is 2,000 times stronger. So even if you put your fingers in there, it kind of hurts. So it gets quite warm. And so we put this UV light source, we shine it on a light modulator. And the modulator is able to essentially project 2D images, like a light projector, in a grayscale manner. And then we have an imaging system here, and the imaging system images the patterns into the resin. And the mathematical assumption what people did in the beginning, and also what we can still do here, is that we assume that the rays are parallel. So we assume they're propagating parallel through, so they are geometric rays. We ignore any effects of, let's say, refraction or even wave optical effects. So the basic assumption, you don't need it. So all the rays are propagating parallelly through. And then the resin we rotate. And then, because of the tomographic fashion, we somehow access the 3D space. So if you're familiar with computed tomography, of course, there's a lot of analogy, right? So in CT, in computed tomography, you rotate a patient and you have like plane waves or straight rays propagating through the patient, and you measure an absorption pattern. So therefore, our theory, of course, is connected to the radon transform. And the radon transform is just a fancy word for line integral through an object. So if you have given an object F, what the radon transform does, it takes your object F and you measure simply the projection of this object along certain directions. So we can do this for the Julia logo, right? So I just load here the Julia logo, and if I now project the Julia logo, let's say from top to bottom, what I observe, I get something like this, right? So if you project the 2D Julia logo to a 1D line, of course, you get just a 1D function. And it still resembles a bit the Julia logo, right? So you can identify the J, but for example, you're not able to know, or you're not able to distinguish if there is a point on top of the J or not, because everything is just stashed together, right? So you're losing a lot of information. So what you need, so the radon transform, just a single projection is not enough. What we need to do is we need to collect a couple of them, right? So if I do another angle, then the projection from another angle would look like this. So 2 projections are also not enough. But what happens if I increase the number of projection angles, I get something which is called the sinogram. And the sinogram is, again, like something, an image. It's an image, but the information is just in a different space, so to say. So we have to we want to revert this. And if you go to CT, like the classical medical CT, what they measure is essentially this. So they have the patient, and what they measure is this. So their task is now, how do I get from the measurement, from the CT measurement, back to the patient, right? So you need something, an algorithm to revert this. And fortunately, there is an algorithm, and it's called the back projection. And the back projection is, again, an integral. And in this integral, what you essentially do is you take your projection and you just smear it back into space. Because in a way, you just forward everything, you stash it together. So if you want to reverse it, you just smear everything back. So let me quickly demonstrate this. So for one pattern, if we do this, what we obtain is something like this, right? So we just smear the pattern back into space. So if we add, of course, this didn't work. I'll have to click on it. Yeah, so if I add another pattern, so this is already 3 patterns from 3 different angles. Now it's 4 different angles, 5 different angles. So I can repeat this procedure. So instead of doing only one projection, I do many projections from many different angles. And if I keep doing this, after a while, you see the Julia logo is coming back, right? It still looks a bit blocky, but if I keep doing this, after a while, it looks better. But let's go to a very high number of angles. So instead of 24, I do 266, and then you see the Julia logo is back. But unfortunately, it looks a bit blurry, right? So since we smear the projections back into space, we just smear everywhere intensity, which is not that great, right? We get only a blurry Julia logo. And in CT, people came up with a clever thing. In CT, they apply a filter, and then this filter somehow magically makes the Julia logo nice again. However, on the computer, you can do this. But in practice, our printer is literally doing this. Our printer has light, and it sends it back into space, right? It back projects it into the space. So the light is putting intensity everywhere. So if we would like to apply this filter here, we would actually need to be able to project negative intensities, right? Because if I smear a bit of light everywhere, I would need to somehow revert it, which only works with negative intensity. But unfortunately, a laser always has positive or greater than 0 intensity, so we can't project negative intensities. So the problem is the filter back projection, which works in CT on the computer perfectly, it does not work in our printer because we can't project negative intensities. So But fortunately, what saves us a bit is that the resin, as I told you in the beginning, you need to put enough intensity into the resin. If you only put a little bit of light, it won't polymerize. So you really need to put enough intensity. So what we say, the resin has a threshold. So it only polymerizes if it crosses the threshold. So let's hope that maybe the threshold kind of fixes this, right? So we have this blurry Julia logo, right? This one here. So maybe if we apply a threshold function, as the physics does, maybe we get the perfect Julia logo. So if we do so, we see, yes, some of the letters appear, but the center seems to be heavily over-polymerized and the J is not even there, right? So we can play around with it, but there will be no perfect threshold to get the perfect logo. So somehow the naive radon transform, it does not work. It makes everything blurry and the threshold function doesn't fix it. So yeah, what we have to do, we have to somehow solve an optimization problem. So what we are given is the optimization problem which we want to solve is what are the images I have to put on my projector such that I get what I want to print, right? So what I do, I build a physical model. My physical model is the rays propagate through, and I have the images which I propagate through. So the question is the optimization problem, what are the back projected patterns, so the image on my projector, and if I project them into the space, I want that voxels of the object cross this energy threshold, and voxels of the void region stay below. And that's the only freedom I have. And if I want to phrase this, I can hope that this works with a gradient descent and automatic differentiation approach. So what I do, I write a loss function. So what I just said in Word, I write in different terms. There's one term, it essentially forces that everything of the object polymerizes, so everything of the object receives enough energy. Then there's the second term, which means that everything outside or not the object stays below this energy threshold, and everything else, we want to avoid here over-polymerization. So we want to avoid that some regions get way too much intensity, because then it gets a bit more complicated. So what we do essentially is we build a physical model where the input are our images, and then we apply, we propagate everything into the space, we apply the loss function, and then we do gradient descent to optimize what are the patterns we have to put on the detector. So just to summarize the physics again, and then we can dive a little bit into how we did that in Julia. So what we put on the detector, or what we put on the projector, is a 2D patterns. And we have many of those 2D patterns. For each angle, we have a slightly different one. And roughly in our experiments, we project 1,000 images. So it's quite a bit. And then each of those images, they propagate through the resin, right? So for, let's say 10 milliseconds, I show pattern A, then I rotate the resin. For another 10 milliseconds, I show pattern B. So all of those patterns, they propagate into the volume, they deposit their intensity, so they put the UV light into the resin, it gets absorbed by the photoinitiator, and all of those patterns, they essentially sum up. So what I get is a summed intensity, which kind of looks like the cross-section of a boat, but only because of the threshold function, which is given by the chemical, physical properties of the resin, only everything after the thresholding polymerizes, so luckily this threshold saves us, and we get the perfect Banshee boat. And all of this, as I said, there's no layers. Since we have the images, everything is projected at the same time. So we don't do layer by layer, but essentially all the layers are encoded into this image. So all the layers just appear at the same time. So what we needed, so of course so this TVAM is a relatively new technique. It's like 3, 4, 5 years ago, old. And in the beginning, actually people, they took the filtered back projection and just clipped it to 0. And they said, it kind of works. But if you look at the edges, it doesn't work that well. So what people developed more recently is that they do gradient descent based schemes. So what we needed in Julia, clearly we needed good optimizers. So there's a couple of packages. I use usually OptimJL, because when I started using OptimJL, there was no optimization JL. For automatic differentiation, I'm still using Zygote. Of course, Enzyme would be nice to try, but I use differentiation interface, and Zygote did not work in our case yet, so I'm still using Zygote. And we definitely needed CUDA support, because we do big optimizations. So just written down here, so as a rough estimate, so the patterns we optimize are HD resolution, so it's 1,000 times 700 roughly, and we have 1,000 angles. So if you multiply this together, you end up with almost 1 billion parameters to optimize. Just to store those billion parameters and doing one forward pass is usually gigabytes of memory already on the GPU. So this is a very big optimization problem. And further, what is kind of a bit also tough is that the 3D radon transform has a computational complexity of n cubed times the number of angles. So it's essentially n to the power of 4. So 1,000 times to the power of 4 is a very big number. So even on the GPU, this takes some time. So on the biggest GPUs you can get, it takes like, I don't know, for this realistic volume, like, I don't know, 5-10 minutes. And later on, I want to show a bit the wave optical stuff, because as I said, right now everything so far was explained from the ray optical perspective. So what we wanted to have this ray optical propagation scheme to propagate the rays back into the volume. But at some point, you also want to use wave optics, because when you go to small scales, ray optics is not quite valid, so you have to use a new physics. So those were the parts we had to create. So a little bit of ray optics and actually more of the wave optics part. So one packages which serves essentially as the backbone for the ray optical parts is Radonka, which is essentially a very simple radon transform implemented with kernel abstractions. So it's like 300 lines of code, and it provides routines for 2D arrays and 3D arrays. And the standard radon transform, which a lot of people use, for example, MATLAB, is just the parallel radon transform and the back project. So essentially the two functions we also need. And more notably, like for the printer, it's not quite the radon transform. Mathematically, it's the attenuated radon transform, because when the light propagates into the resin, the ray gets absorbed, right? It loses a little bit of intensity. So the mathematical correct term is the attenuated radon transform. And if you Google this, there is no implementation in any of the languages. So no one's using an attenuated radon transform. So you can do a hacky version of it, but then it's very slow and very memory intensive. So we also had to implement this attenuated radon transform. And in a way, what's pretty cool is that everything is essentially a very flexible attenuated radon transform. And if I don't use the attenuation, you simply set the exponential factor to 0, and then nothing happens. So in a way, Radonka is a very flexible package. And even though it's very flexible, it still can compete with Astra, which is a very common CT library. And it also beats MATLAB if you use CUDA, because radon on CUDA and MATLAB doesn't work. Or it's not very fast. It works, but it's very slow. Just to show a bit the flexibility of radon. So with Radonka, I can essentially specify what geometry I have. For example, in this case, it's a parallel geometry. This is called the parallel radon transform. However, sometimes I don't have parallel rays. I have some rays which are bent. Then this is called like cone or fan beam tomography. So I can just specify that, and at the end, everything runs very well. And actually, in our printer, we use more often this cone tomography, because if the rays hit our round glass vial, they actually get refracted. So they're not propagating parallel through the resin, but instead they're getting refracted towards the center. So most of the time I'm actually using this one. And it's so flexible, then you can also play around with, I don't know, to do very funky geometries, which none of any other packages I've ever seen supports this. So for us, this is very flexible. And also the good thing is, if I run this on CPU, right, I can just run it. It's multi-threaded on like 24 cores, but if I run it on a GPU, it's much faster. So in this case, I don't know, 30 times or 20 times faster. So that was really important for us, that the CUDA performance is good, because we have the big volumes. So we needed this performance. And this is all implemented in kernel abstractions. I can just highly recommend this package. Very easy to use and very great performance. I mean, I'm not a CUDA expert at all. I'm just using it, but it just works. Another package we implemented, then more tailored around the problem of TVAM, is called Swiss VamiKnife, and it's the only toolbox I need for tomographic printing. And it can include the physical properties as the absorption of the resin, because if I put more photoinitiator, I have more absorption. If I put less photoinitiator, I have less absorption, but then I also need to print longer, because I need more time to accumulate all the intensity. It supports different geometries and also ray and wave optics. And the way it works, from the user point of view, in the beginning, you would just specify your target geometry. So in this case, I want to print the Julia logo, so I specify the 3D target geometry. What I show here is just one of the cross-sections. Then I define the loss function, as I explained in the beginning. So I have this thresholding of the different terms, so I just define it here. Then I define my optimizer. In this case, it's gradient gradient-based. We also offer some iterative methods, but most of the time I'm using gradient-based with an LBFGS optimizer, 15 iterations. That's good enough. Then I need to specify the angles, right? Because depending on how much I rotate, I'm able to show more angles or less angles. I specify my geometry, especially this is a very critical parameter, the absorption of the resin. And at the end, I just call optimize, and it will optimize it. And what I can do, so for example, what I'm showing here is that would be the final patterns I would show on my projector. So we can look at them from different directions, and you see it looks kind of like the Julia logo, right? So it's usually you can interpret those patterns very well, but to calculate, especially here, sometimes you see at the edges, to really get the precise intensities, you have to optimize it. So there's no way you can avoid this. Another funny physical effect is if I increase the absorption quite a bit, what happens physically is that the light, it propagates through the resin, but it doesn't reach the center because it gets absorbed on the outer region. So the red region means a lot of light is deposited. So in practice, if you put too much photoinitiator, you can't print because your light already gets absorbed on the outer shell of the glass vial. And this is actually what they do in an SLA printer. In an SLA printer, they put a lot of photoinitiator into the resin because they print layer by layer, and they want that the light doesn't propagate deep. They want that the light essentially gets absorbed in the very thin layer at the top. So that's why they put a lot of photoinitiator in their resin. And in our case, we do like really a lot less, like, I don't know, 3 or 2 orders of magnitudes less in photoinitiator to avoid that, because we want that the light propagates through the resin. Yeah, exactly. So this is all the ray optical part, but of course, I mean, this ray optical part people did before, so this is kind of reproducing existing science. So what I did in my PhD, we were like, thinking about, okay, let's try to push the resolution of those printers, because 150 micrometer is great, but there's printing technologies which can print 100 nanometers. So can we push in this direction? And for that, we developed a wave optical framework, and of course, we needed it to be differentiable. As I explained in the beginning, all the optimization is based on gradients, so we needed a physical model, a wave optical model, which we can differentiate through. And for that, we created the package wave optics propagation, which provides the routines for free space wave propagation. And if you ever worked with wave optics is way more expensive than ray optics, because in ray optics, the rays, they just propagate through and they don't talk to each other. But in wave optics, everything talks to each other. Like in wave optics, their borders, they morph to each other, you have diffraction effects and stuff like this, and those are global effects, so the pixels have to talk to each other. And what you use in the backend is like FFTs all over the place. So we use a lot of FFTs, and to avoid that this is very slow, we also had to create a lot of memory buffers. So to use the wave optics propagation, what you usually do is you create a type where it essentially stores a lot of buffers, it stores all the information, it pre-plans the FFTs, and you do this only once, and once you call it, you just run it, and then it executes the wave optical simulation. And this is a bit of a pain. I have to say in Julia, it's a bit of a pain, because to get it fast, you have to use the memory buffers, but then automatic differentiation with SIGO doesn't work anymore because it's in-place mutation. So essentially, we had to write a lot of the gradient rules ourselves. So, and I know a lot of people in our field, they're just using Jax or PyTorch, and it just works a bit better, honestly, there. So it's a bit of a pain, but at the end, it kind of paid out. So because we could also make, actually algorithmic improvement on the backpropagation. So at the end, I actually needed chain rules to make also the algorithms better. So I couldn't avoid it anyway, but it was a bit more painful. And what I can so what I can do here is I can simply compare the wave optical part and the ray optical part. So what you see at the top, at the bottom, that's the easy one. That's the one we discussed in the beginning. That's ray optics. So the ray optics just propagates through the resin, and the rays just are straight. There's no way that they deflect or whatsoever. But in wave optics, if you propagate a wave through a resin, what you see is that the edges, they slowly morph, right? So in the beginning, it is a sharp edge, but then after a while, it kind of blurs out. And the cool thing is, if we now compare this, like our ray optical and wave optical simulation, so the top part is just L here is 10 millimeters. So if I want to print a boat with 10 millimeters, if I look at the ray optical simulation and the wave optical simulation, they both give the same result, because in the limit of large structures, wave optical and ray opticals are the same. So that's good. It's a good check that everything works. But if you go to smaller structures, for example, a boat of 1 millimeter or a boat of 100 micrometer, so 10 times smaller, you see at 1 millimeter already that the ray optics starts to fail. So some of the features are missing. And if you go to the very small scale, like 100 micrometer, you see that ray optics is simply not, it's not the correct physics anymore. So this is all simulation. It's not proven in experiment yet, but it's clear. At some point, ray optics is not correct anymore. But what's the cool thing is that if you use the correct physical model and you optimize the patterns with the correct physical model, it shows that in theory, it's still possible to print in the region of this, it's a 100 micrometer boat, but the features are much smaller. They're like 10, 20 micrometer or even less. So if you use the right physical model and you just optimize the patterns on the right physical model, you are able to print much smaller features. I just skip over this part. So at the end, I just want to summarize with our packages, essentially Swiss Wami knife, Radonka, and wave optics. We could essentially show that TWAM is able to print at small structures, and we had to develop quite a bit to be able to show so. And I really want to give a shout out to some of the packages, especially kernel abstractions. It's really great for Radonka. It's amazing for me to use, and it's a lot of fun to write and very easy to write. That's it, and I'm looking forward to your question.
Yeah, really cool. Thanks. So with the extra work you had to do to get AutoDiff to work, have you now fixed it for everyone, or is this like an ongoing problem? Are people going to have to keep adding to that?
So I think it's just the fix for me for the wave optical stuff. So it's just in my package that I registered a custom reverse rule and to fix essentially my forward pass.
So yeah, what things did you have to add rules for?
So like I think I have the code here. So the problem is really like my forward pass looks like this. So I use essentially existing buffers, I do a bunch of FFTs, I shift them around, and everything is in place to not allocate a lot of memory. And Zygote on this immediately fails, right? All of this is in place. And then I tried with differentiation interface enzyme, and it gave up. So I think that the problem is really the in-place mutations all over the place, like IFFT shift, I do multiplications, and even the FFT isn't in place. So really, so this line of code actually, it only allocates once at the very end where return a new array, which is just a new, not a view, but a proper copy. So and this part of, so essentially for this, I had to rewrite the reverse rules myself.
I suspect that Enzyme struggles with the FFTs because I imagine that you're just calling the FFT library or the CUDA one or the...
Yeah, probably. So I'm also not sure because in this case, I'm using complex numbers, CUDA, and FFT. So I mean, it's a lot of knowledge. I think, there's a question over there.
I guess you assume coherent wavelength everywhere.
Yeah. So for the wave optical simulation, that's all coherent. Yeah. So
you can assure that because you're using a laser, right?
So that's why it makes it difficult to do that in experiments, because we are using a DMD, which actually does not a grayscale modulation, but it does a time-modulated grayscale modulation. So with our setup right now, I can't use my theory, because the setup, what we do, it actually would require a binary optimization. So it's a bit tricky. So you could implement this with different hardware devices, but then at some point you realize the glass vials, the best accuracy you can get for glass vials in precision of the wall diameter is like 100 micrometer, 10 micrometer maybe, but if you want to print at 1 micrometer, your glass vial is simply not good enough. So it really is an engineering problem that our round glass vials are not precise enough to use that theory. So we really struggle that our hardware is not good enough for the theory we would like to use.
Thank you.
I think one more over there.
Thank you very much for your wonderful presentation. Could you please give more details of how you use the kernel abstractions to implement the radon transform?
So I think the radon transform might be a bit too much, but I have an example on the differentiable image rotation. So there was also no differentiable image rotation in Julia, but we just implemented one on the way. And kernel abstraction is very easy. So you have a normal function. So the imrotate, you would give it an array and an angle. And at the end, for the kernel abstractions, you need to require backend, which in this case depends on if it's a CUDA array or normal array. And then you have this kernel. And the kernel is essentially called here. And what I do in this case, instead of having two for loops where you essentially have a for loop for j and for I, instead you have this kernel abstraction specific statement where you essentially extract the I and the j, and then you just run your kernel. and that's it. So essentially transforming your code instead of using 2 or 3 nested for loops. So in my case, they're all independent of each other, so you can parallelize it. Instead of using those 2, 3 nested for loops, you use kernel abstractions, you put this statement, and that's it. So it's very easy. So I really recommend to check out the documentation of kernel abstractions. It makes the life very easy. And it runs on GPUs, CPUs, technically also metal GPUs. However, we tried last night, didn't work, but yeah.
Thank you.
I think there's one question.
Out of curiosity, on your experiments, how is like work holding happen for something? Because I imagine you have your resin in a vial or something, and how do you hold the piece of work?
So essentially everything is embedded in the resin, and so for that we have a drill bit holder. So the vial is like, it's 16 millimeters in diameter, so it's a small glass vial. We essentially put it into our drill bit holder, we fix it, and then we just rotate our stage. So if you're interested, there's also a paper from another group where they assembled this for like $500. So it can be done relatively cheap, but yeah, it's a bit technical. It's not as easy as a SLA printer, and the community is not as big. There's also some companies popping up right now. But yeah, so technically you can build one yourself for like maybe 500. But you also need some light source, but you don't need a laser. You can also use a high power LED, but still watch out for your eyes. So it's dangerous. You mean a printer or a printed thing? The printed thing is actually, so it's very small. So, and also this, so printing the Julia thing is not quite impressive because it's a disconnected thing. So if you print it, you just have all the letters all over the place. And also it's very small. So I should have given you some boats, but the thing we're talking about, it's small. So it's not very impressive to, and it's also a bit sticky, and sometimes the things we use, they cause cancer, so. But we can actually do bioprinting. So if you're in biology, and one of the big and promising applications of this printer is actually bioprinting. So recently in our lab, we printed parts of a pancreas, like parts of the human pancreas with cancer cells, and then you can do 3D studies of cancer growth and stuff like this. So bioprinting seems to be one of the promising applications, but also optical components and stuff. So yeah, the technique is relatively new, so there's more and more applications popping up.
All right, thank you.
Thanks a lot.
All right. We have a final presentation here before the final keynote of the conference. So right now, Mason with what's next for transducers.jl. Please take it away.
Thanks. Okay, so transducers.jl is a package that was written by Takafumi Arakaki, and it's based off a concept that was developed for the Clojure language by Rich Hickey. I'm not either of these people, but I've been trying to maintain transducers.jl, and I want to talk a bit today about kind of how transducers works under the hood, what the actual mechanism is here that's novel, and then kind of what sort of challenges I've been facing while trying to maintain it, and then what I would like to have done in the future. So the basic idea here is that lots of programs that we like to write, especially loopy ones, can be described as some sort of process where we take in some collection of data, we do something with these chunks of data, and we produce some result. And often, almost always, when we're doing this, we're conflating a few different things. So what type of container is actually holding my pieces of data? What am I trying to do to that data? And how is it being scheduled? Like, am I doing some sort of sequential loop? Am I trying to do some sort of SIMD thing, distributed, threading, GPU sort of thing? These things are often all kind of mushed together in people's code. And transducers is one kind of interesting idea for how to disentangle these three things, and with a goal towards kind of letting users focus on what they want to do with their data, and just write one transducer that describes what they want to do, and then reuse that transducer for a vector, a tuple, a channel, whatever, and have many different execution models that the transducers library would focus on. So we can, at the library level, we can focus on being very generic with having backends for sequential, threaded, GPU sort of backends. So, okay, before I talk about transducers, I want to introduce a bit of background. So reductions is one of these kind of scary comp sci things that people start trying to describe and everyone's eyes glaze over, so I'll give it a shot. We have this function in Julia called foldL, and this is really just, at the end of the day, a kind of structured way of describing a loop. So when I say foldL with this function op, this gets lowered into basically initializing some sort of state, looping over my collection x's, and at each step of this loop, I want to update my state by applying this operator to the previous state and the element. And then I just return the final state. So this is a very generic process that can describe pretty much any loop, depending on what op is, right? And Julia also has this function reduce, which is for the cases where you don't care about the order, or really the associativity. So if you don't care if I go forwards through the loop, or backwards through the loop, or pairwise through the loop, then typically you want to use reduce, because then Julia is free to choose like some sort of pairwise scheme that maybe reduces error or something like that. And this is very abstract, but I think almost everyone in this room should be familiar with at least two reductions, which are sum and prod. Sum is just reduce with plus, so you add up every element in a list, and prod is just multiplying together every element of the list. And so you can kind of go from there and build up an intuition for how these things should work. And then this is just a little diagram showing like, this is how you kind of contract together elements with foldL, and with reduce, you might do some sort of pairwise thing like this. And this is why reduce is parallelizable, basically, that you can do this reduction at the same time as you do this reduction, and then you combine them at the end. And these two things will be equal if this function op is associative. The other bit of background I want to describe quickly is iterators. So we have these things in Julia called iterators, and this is kind of the typical way of describing some sort of lazy transformation over data. So you wrap some sort of collection with the iterator, and then the iterator redefines what it means to take elements out of that wrapped collection. So, like as an example, we can define like a filter over the range 1 to 10, where we filter out for the even elements. And if we write some loop over this iterator, we see that the loop only sees these even elements, 1, 2, 4, 6, 8, 10. The reason this works is that Julia's loops really just desugar to something that calls this iterate function on the elements, and then it just keeps on going in a while loop until iterate returns nothing, and then it finishes. So these iterators are state machines, and they use this function based out iterate to pull values through some chain of nested iterators. And this whole process is kind of essentially inherently sequential, and it can often be inefficient. There's ways around these inefficiencies, but it kind of requires some gymnastics and a lot of knowledge of this deeply nested structure to make efficient. So as an example of how these things can be inefficient, if you want to add up, say I have some filter over the even numbers in some collection, and then I want to double each of those filtered results. What a standard implementation of foldL would end up doing is this kind of double while loop, where you get stuck in the first while loop, and then you fall into this inner while loop, and you keep on iterating until you get an even number. Then you break out of that while loop, you double things, you add them up, and then you go back into the inner while loop, which is probably not what you would intuitively write, but maybe a sufficiently smart compiler will fix it, blah, blah, blah. With transducers, we instead of defining these map or filter things that act on data, we have these uppercase map and filter transducers that really end up transforming reducing functions. So what using these things kind of looks like is you might use this fold XL function that comes out of transducers. And this thing is basically describing some way to transform this plus. So you can also write this alternatively in this kind of pipeline fashion. So you say 1 to 10, filter is even, and then sum up. That's another way of writing this. And you can also compose transducers with this syntax I'm maybe not the biggest fan of, but I'm going to kind of focus on this kind of a bit more verbose syntax here instead of the pipeline syntax, because it's for the purposes of this talk, it's a bit more clear as to what's going on. So, and also you don't really necessarily need to use this floops, all this syntax, because we have packages like floops.jl for using for loop syntax, if that's what you prefer. But anyways, what's going on kind of under the hood here, and what makes us different from an iterator, is that we're actually not transforming the data, but we're transforming the functions. So when I try and apply this transducer XF to some fold, I create new reducing operators. So first, we apply this is-even transducer to my reducing operator plus. And this creates a new reducing operator. I'm calling RF prime here, that takes, and this is just a 2-argument function that takes some state and some element. This is the body of the while loop, or the for loop. And it just checks, is x even? If so, I'm going to apply this reducing operator, in this case plus, to add the state to x. If it's not even, I just return the state. The state is unchanged, right? Because I'm filtering out this thing, so I don't want to change the state. And then we can apply the map transducer to this transformed reducing function. And instead of acting on the outside, this actually goes to the inside. So I still check is even, but I'm going to now add state to double x. So, and the way we're kind of able to operate from the outside in here is that these transducer objects, so if I take map and then apply filter to it and then apply all that to plus, I get this kind of structured object that's a reduction map of a reduction filter of a reduction plus. And yeah, this is just a structured thing that the transducers library is able to take advantage of for various things. But and so basically what ends up happening here is that if we compare that to the code generated by the iterator sum of the filtered loop, we get something that's much more like what you would actually want to write, or what you would think to write by hand. Now it turns out that Julia, if you try this, Julia will actually generate this code, but that's because Takafumi submitted a PR that detects filter map and then makes it do this one instead of the other one. But a naive implementation of fold-L would do this. And what's nice is that we can, if you use transducers, you can just do this with function composition instead of hoping that your compiler detects that, oh, if you have a double while loop with a break, then that's actually an if statement and blah, blah, blah. Okay. So the other thing that's really nice about these transducers is that because they're just functions, we can apply them kind of wherever we want with whatever schedulers we want. So here's, the filter is even with map that's going to tell me, okay, I had some element I on some thread ID. So if I put this in fold XL, we get what we expect. We get 2, 4, 6, 8, 10, all on thread 1. But there's also this fold xt, T for thread or task or whatever. And if we use that as our kind of scheduler here, we get 6, 8, 4, 2, 10 on thread 2, 3, 5, 4, 1. So this is easily multi-threaded. And it turns out that you can also use a distributed scheduler, so fold xd for distributed, and we get worker 6, worker 4, worker 2, worker 5, all kind of sufficiently out of order. So using these reducing function transforms, instead of we kind of decouple from the data and we let schedulers worry about scheduling. We get the users worry about what my actual function is, and in some ways it's kind of similar but different to the ideas in these kernel transforms as well. But yeah, and we also have, there used to be a GPU like a CUDA plugin that could compile these things to GPUs. It's not currently working. Hopefully we can get that working in the near future. And yeah, one of the other advantages of these things is that these transducers can kind of define traits on themselves that tell you information about what they do. So we have transducers that, like map, is a size-preserving transducer. So if you just have map and I don't know, like enumerate or something, then you know that whatever collection comes out of that series of transducers will be the same length as the collection that went in. So if you're doing a collect, you can pre-allocate an output that's of the appropriate size. If you have map and filter, then we know that the collection is going to be smaller than the original collection. If you have map and map splat or something, or map cat, then it might be larger than the incoming collection. And also, we know that some transducers carry state, like enumerate. And so if you have a stateful transducer, then you know, okay, I can tell the user right away, that's not parallelizable. I can't put that on fold xt. So unfortunately, not everything is sunshine and rainbows in transducers land. So there's kind of a whole ecosystem around these transducers packages, and they all only had one maintainer. And when that maintainer kind of disappeared, which is something that happens in open source, there was a whole constellation of packages that were kind of suddenly orphaned and had couldn't receive updates, and didn't really have anyone to give them updates. So I eventually have been taking over these packages one by one as they need updates, moving them over to a new organization, and reworking everything to get them running again and accept patches. So thanks. Well, so I don't pat me on the back too much because I haven't been doing that great a job of it. But one thing that's quite nice about this is that even though on the logistical side it's quite a pain, PKG, like our package manager, makes this seamless for users. Users can just say update transducers and they'll get the new version from the new repos. But if you do find yourself maintaining an important package on your own, please consider giving shared ownership to at least one other person so that if you suddenly disappear for whatever reason, other people can continue your work. So the other kind of major problem, other than all these logistical challenges, is just that the code base itself is quite large and quite complicated, and it evolved a lot over time. So a lot of this was written in Julia 1.0, and there's all sorts of tricks for avoiding the fact that we used to have allocations from having a mutable struct inside an immutable struct and stuff like this, and so there's a bunch of tricks that might not even be needed anymore. But then there's also things that definitely are needed still, and if I remove them, stuff breaks and stuff like that. So I've been having a lot of challenges trying to understand what to do, like how to fix things in this code base. So I'm currently working on better understanding all these internal mechanisms. I was hoping I would be able to show off a bit this simple transducers package I've been writing, but it's not currently in that sort of state. I haven't had as much time as I had hoped. But the idea here is this might end up being kind of the future of transducers, or it might be kind of just a project that I use to better understand, okay, how do all these mechanisms really work? I can go through line by line in the original transducers and see, is this something that's necessary for like a simple version of this package? Move that over if it is. If it's not, just leave it. And I can also hopefully use this as a learning tool, because I've had a lot of people come to me and be like, hey, I'd like to help out, but like, I don't understand what's going on in this package, and I don't understand either, so I can't really teach them. So hopefully with a simple transducers package, I can show people that and have that as a bit of an onboarding experience for people. The other thing is that the APIs kind of grew organically. So like we have fold XL, fold XT, fold XD for thread or sequential threads and distributed, but then if you want to do it on the GPU with the broken GPU package, it was an executor interface and you had to do something else. And so I'd like to start kind of unifying some of these things, fixed naming, stuff like that. There was also another package that maybe would have been a better idea to present here, which is Oh My Threads. And we learned a lot of performance lessons. So this package was heavily inspired by transducers, but then we learned a bunch of lessons while implementing it that I think can speed up a lot of certain multi-threaded tasks in transducers. So I'd like to bring some of those lessons from Oh My Threads into transducers. And then, yeah, I'd really like to get this folds CUDA thing working again, because it's always nice to be able to run things on GPUs. And finally, I'd like to, put it out there that if you think this sort of stuff is interesting and this is something you'd like to help out with, it doesn't need to be a big job, but reach out to me. Maybe I can try and find something that I could get you started on. So, yeah, that's it for me.
Thank you. Any questions already? I see multiple hands.
Hi, thanks. I was wondering, this dream of back-end agnostic execution reminds me a lot of Dagger, which we learned about at the beginning of the week. Is there any collaboration or interactions going on there? And if not, why not?
Yeah, so I think Dagger is actually a great candidate for kind of getting plugged into this whole transducers world for a couple reasons. One, it'd be nice for transducers to be able to, so I think we already have a okay scheduler, but I think Dagger has a much better schedule for distributed stuff, so I'd like to use that. But also, I was talking to Julian about this, and he really wants users to be able to write a for loop as well. And with transducers, we have this floops package that can turn some complicated series of for loops, even with continue and break, and it can turn that into a series of transducers. And so if we get a executor for Dagger working with transducers, then I think that's something that both sides would benefit from. And it's something Julian's interested in, it's something I'm interested in. So hopefully that can happen in the near future.
In the graphs world, there's been this like light graphs package, then then became the new graphs package. Is this how you also imagine simple transducers?
Probably not. I'm hoping that, so it kind of depends, I guess. So one of the things that makes me kind of want to focus on simple transducers right now is that transducers.jl has like 20 different transducers it defines, like map, filter, has all these very complicated ones, and I don't really want to think about most of them. I just want to think about like a small subset of them and a small subset of foldables. But I'm hoping that depending on how things go, I can just start learning lessons in this simple package and then bringing them to the more complicated one, and keep the simple one as a learning tool for people or something. But it might end up being preferable to just move forward with the simple one.
Okay, but like maybe ideally simple transducers will never be the package that people are recommended to use primarily.
I don't know yet, but probably not, but it's certainly possible.
All right, thank you.
Is there a chance for false kernel abstraction?
Yeah, yeah. Actually, yeah, I guess so. I think when Folds CUDA was written, Folds kernel abstraction was, kernel abstraction might not have existed or was quite immature. So probably if I have to do a full rewrite of Folds CUDA, it would be a Folds kernel abstraction, but might be able to just fix a couple low-lying things and get Folds CUDA going. So maybe that's the way to go in the near future, but definitely interest.
So this is kind of a follow-up question. So does the Folds CUDA breaks because they are just because like the maintenance issue, or there are some kind of a technical issue that cannot be solved right now?
Folds CUDA was never mature. It was always kind of in the early stages. I think he started it not long before Takafumi disappeared. So there's probably some of that, and I think also that CUDA has made some breaking changes and stuff like that. Like I think CUDA was not on as firm footing back then as it is today, and so I don't actually fully understand what broke, but I assume it's just some classic bit rot where, oh, we made a non-breaking change, but like everything broke or something. I don't know, but we'll see. I think there was a question in the back, or okay.
Yeah, maybe not so relevant anymore, but I was curious about folds.jl, which is, I guess, can you comment a little bit on it? It's a subset of transducers, I guess, or built on transducers,
Yeah.
but I guess shares the same issues with, in terms of maintenance and so on.
So folds.jl is basically, I don't know what happened to my thing, but it doesn't really matter, I guess. Folds.jl basically just tries to give people, instead of having to use this fold X whatever and a transducer, we just give them, folds.map, folds.sum, folds.reduce, and it will lower the transducers under the hood. We have ported Julia Folds or folds.jl to the new organization and want to keep supporting it. So for people that prefer the folds interface to the transducers interface, yeah, it shouldn't be too hard to keep alive. And yeah, we'll just keep on working on it as long as I can find time and people are interested.
So you mentioned about the traits. So for example, you mentioned like maps has a fixed length kind of. How is that implemented?
It's just dispatch. So I think basically there's just a function that's defined as like is size conserving, and then the method on map is it says size conserving. No.
I wanted to ask, why did you take over Transducer's ecosystem? Like, very grateful that you are, very happy about this, but I kind of wanted to know what's your motivation?
Yeah, so I think I just kind of, so it's maybe not quite as relevant today, but I think definitely when this whole transition was happening, there was no package I could recommend to people other than like the transducers based stuff if they just wanted to do multi-threading over some array, right? Like multi-threaded sum, multi-threaded for each or whatever. Base.threads has some great primitives that is not a good end user experience. So that was one of the main motivations, and I also just find transducers to be a very interesting idea that I think hasn't been fully explored, and I would hate to see all this really brilliant work that Takafumi did. I would hate to see that go away, so I kind of just wanted to keep it going.
So, all right, that's it for this track. On some of the screens, there was a mention that the keynote would start at 5:30, but we're actually trying to start it at 5:10. So take a quick bio break if you need it, and then please make your way to the main stage.